Okay, hello, good evening. We are still waiting for one of the judges to join, but we can make a start with the introduction for 10-15 minutes. And then we can start the first presentation. Hopefully by then, Rebecca from Net Zero Technology Center, the third judge will join us. So my name is Houman Takhtichian. I'm past ICOR Aberdeen chair, and we were running this program since January this year. So waiting for this evening to come so we can conclude this program and see all the presentation on the case studies. So I will just keep it very short because we have very tight schedule today with 6 presentations, each presentation 20 minutes. So we actually are trying to finish on time by 8:30 for the final decision and the announcement of the winner. So just a quick one about the agenda today. So after this introduction, Steve Patterson, he will do an introduction about the program and the case study. And then we will decide about the order of presentations because we decided to go for a hat draw to decide which group will start first for the presentation. Just to remind you that each presentation is 20 minutes, followed with 5 minutes question and answer. The questions are coming from judges only, and we are not accepting at the moment any question from online audience, just to make it fair for all groups. And there will be 5 minutes for change to another slide set and next presentation. During the presentations, only the group who are presenting can stay in this room. 3 chairs here, so I expect most of the groups will do 4 of them will contribute to the presentation. So you can all sit here and one presenting at the same time. And just remember your order and be behind the door maybe 5 minutes before, so we can have a smooth transition to the next presentation. And we will have a coffee break 5:45 after the third presentation, and then there will be a buffet dinner after the 6th presentation and before the decision made by judges. Again, we do timekeeping for the scoring purpose only, but for your timekeeping is up to you and your team to make sure that you are finishing right on time. And you probably have already heard about the scoring method, that every 1 minute you will, if you go over your 20 minutes, you will lose some points. And hopefully by 8:15 we finish, and the winners will be announced by Stephen Tate, ICOR president. And that's all from me. With that, I hand it over to Steve for his introduction to the case study.
Okay, welcome everyone. I think we kicked this case study up on the 2nd of June, and I know that you've all been working extremely hard putting together, analysing, putting together your presentations this evening. So I'm really looking forward, I think, to 6 fantastic presentations. The case study is essentially was based loosely on an existing platform in the North Sea. The idea was to really look at the current conditions of that platform, to analyse it, to come up with recommendations, to look at possible influences such as a new field that's coming online, slightly sour. So again, some issues there around about that particular change in production. There's really management of change needs to be done, but also any other sort of innovation ideas you might come up with, particularly in the light of this current push towards net zero. And then, clearly how you react, how you relate to the actual clients through the integrity services contract. So the judges tonight, Sue and Chris and Rebecca, if she makes it, essentially they are the integrity service contractor, and they will decide who will actually get the job for the client. So that's how you should be pitching it. You're not pitching it to the client. The instruction is very clear. You're pitching it to the contractor, the go-between, as it were. So before I go any further, there are 6 teams. I know that one of the teams only has 3 presenters. Alistair, how many on yours? 3 as well. Okay, so in that case, we're going to essentially draw from a hat the who will go first, second, third, and so on.
Oh, it's on online. It's not working. Oh, it's for the online. Oh, okay. Right, 1 to 6 then on that.
The name.
No, 1 to 6.
You're already here.
Already here. Oh, yeah. Okay. Thank you. They've been prepared earlier. Thank you. Okay. So the judges, they've been given all the material that you've, as participants, have received. Okay. They've also been given some guidance on marking, and it's really up to them ultimately. Purely guidance. That was also circulated, but we're looking at how you've analysed the problem, how you've proposed mitigation of the potential problems. Thirdly, how you manage the change and innovation, and thirdly, how you have interface with the client, and also how you actually present. So the presentation is quite important. As Human's indicated, we will penalize people who go over by more than a minute, because 2 years ago, at least one of the presentations was 25 minutes long, and I think we need to keep a level playing field. So once you go past the 1 minute grace, you'll be losing points. Okay, so do keep to your time. Okay, really important. And I will actually give an indication when there's 2 minutes left. So I'll be at the back and I'll wave when there's 2 minutes to go. Okay, so you will get a warning. Okay, and then when you get to the minute, I'll be waving madly. Okay, so so that's when you start to lose points. Have we got any questions before we go any further? Is it very clear what you'll be doing? And we are going to draw the team, so it's completely fair again as to who goes first. Some people feel it's a disadvantage, others, yeah, they're so well prepared it doesn't matter. Okay. That should be the case. Rebecca's not here, so what are we going to do? We just go with we can start with the draw. So there's right, the team that's going to go first is Group 1. It's first, that's easy.
Group 3.
Group 5.
That's 1, 3, 5.
6.
1, 3, 5, 6. Who's in the dance off?
Group 2.
Make sure they got the right number. And then the last one is group 4.
Group 4. Okay, so very shortly we will ask Group 1 to stay so that they can kick off their presentation. Just very briefly, I was giving Rebecca a few more minutes. So the judges tonight are Sue Cushnigan, who is the Maintenance and Integrity Manager at Shell UK in Aberdeen. So And we have Chris here, who is BP, also a integrity lead.
Yeah, senior advisor for Crown
Yep.
in Sunbury.
Yeah, in Sunbury. But you, yeah, so Chris. And Rebecca is, she's not here yet, but if she does turn up, which I guess is going to be a bit awkward if she doesn't see the first presentation.
Should we propose Steve Kane in case?
Steve, if you're happy to do that.
Wait 2 more minutes.
We can,
Does anybody know where she is? Does anybody contact her? No, I know, guys, she might be 2 minutes away, but she also might be an hour away.
yeah. Yeah, try and, have you got the number? So when, apparently there's another room upstairs, which, okay, so you know where to.
Your group and the time that you have to be here and stay in the room of the waiting. And just remember, I know that you have already received the invite to the Zoom online. You are not allowed to watch the other presentation while you are in the waiting area.
Okay, any more clarifications? Everyone happy? Knows what they're doing? So it's, was it 1, 3, 5, 6, 2, and 4? Yeah, that's the sequence. Sorry?
You were keeping a track. Oh no, so it was 1, 3.
1, 3, 5, 6, 2, 4.
Yeah.
Thank you, Stephen. Like all good corrosion engineers, you're double hatting tonight. So, in which case, I think if we can therefore ask everyone, but Group 1 and obviously mentors are welcome to stay if they want to. Up to you.
So we don't want, and then at the end. Let's just go through. Oh, okay, we can read here. Yeah.
We're ready? Or- Hello, everyone. Are we okay to go? Yeah, okay, so, we are group one. I'm Ross. We have Steph, Stuart and Austin. They'll introduce themselves when they come to speak. Basically, we are group one and we are here today to propose how we are going to kind of optimize the integrity management of the Solaire platform. For a little bit of background, the end life of the platform is 2032. It has been operational for around 15 years now. From the information we have been given in regards to the Solaire platform, we've done a high-level risk assessment, which we'll go into more detail from. This high-level risk assessment does have a few assumptions that we've made, and what we do to kind of propose to how we get around that is once, if we were awarded the contract, we were to do a full risk-based analysis to start off with. This would help us kind of understand the degradation of the platform a bit better, and also, as I said, fill in any assumptions made in the initial risk assessment. What we would also like to do is implement a data management software just to help us with the efficient running of the platform as well. Just again, with the change of ownership, we do believe this could raise an issue with passing over of documents kind of within the admin side. And we believe having a software, a data management software along with the risk-based software could help alleviate any potential risks coming from here. What we'd also like to propose is we've done our due diligence and believe the new field to be economically viable. So what we'll propose on our presentation here is how we plan to move the hydrocarbons from the field to the platform until we plan to deal with the issue of the new field being containing H2S being slightly sour, and with the Solaire platform being a non-solar platform, we're going to propose how we're going to combat that. I'll pass you over to Steph now, who will go into more about the.
Thanks, Ross. So in our opinion, the greatest risk to any asset is, sort of in terms of corrosion risks, is poor integrity management and corrosion management. So if we get the opportunity to work with yourselves and the client, we would look to undertake a thorough review of the existing strategy to establish what has been done well and what needs to be improved on. If not already in place, we would recommend moving towards an industry standard strategy such as the Energy Institute or the IOGPs. This is with the aim to have sustainable good practices in place. We would also look to move towards a risk-based approach to ensure that the highest risks in the asset are being managed appropriately. We would look into different data management systems, as these can increase efficiencies and risk visibility. They can hold and aid the management of key information such as COI and dead lag registers and the anomaly management. If not already in place, we would recommend introducing integrity operating windows or IOWs. This aids the corrosion management and in turn should result in reduced inspection frequency. The data management systems can also collate when the IOWs are being breached. This not only highlights when they're being breached, but also helps a feedback loop to prevent these breaches in the future. The data management systems aid visualization and data sharing, and this helps decision-making and discussions, not only within the corrosion or IM team, but also with the asset and business management, which will be key in the initial phase of new ownership. As well as the wider strategy, we wanted to establish if there were any specific corrosion risks on the asset. We reviewed the data to establish different internal and external degradation mechanisms and the probabilities of these occurring. For the consequence, we looked into the impact in terms of safety, production, and the environment. We used this approach for each of the line items on the Excel sheet that was provided. And the results gave the risks, as you can see plotted on the matrix. There are quite a lot of risks in the bottom right-hand corner. However, there were conservative assumptions taken. Therefore, with additional data, we would expect most, if not all of these to move within a more tolerable region of the matrix. From the risk assessment, there were 4 key corrosion threats noted in the high and extreme areas of the matrix, with CUI being approximately 50% of these. However, as I mentioned, there were conservative assumptions taken, and this included us assuming there was insulation in place, even when it was an unknown. As you're aware, CUI management is a significant challenge with a great deal of time, effort, and money spent across many industries. We would look to work with our processes and colleagues to establish where there's insulation, what condition it's in, and if there's any insulation that isn't required. We would also look to work with the inspection contractor to establish and ensure the most appropriate techniques are being used during the offshore surveys. Through our processes, our aim is to improve safety, reliability, and efficiencies across our plant, not only the existing plant, but also the new equipment and pipeline for the new field, which I'll pass on to Stuart to discuss further.
Right, thanks very much, Steph. So we mentioned already that we have this new reservoir, potential to access this new reservoir, but it's some distance away from the platform. So what we were thinking, well, we're going to need to have a new pipeline to flow these fluids back to the platform. So similar to how we kind of plan to manage the topside risk, we also plan to have a kind of a risk-based approach to the design and then operation of this new pipeline. So I've got a little graphic here. I don't know if it's too easy to read, but we are going to be, we'll start off with the definition. So we need to define the requirements of what we need from this new pipeline. We need to do a quick risk assessment to determine the main threats that we're going to be facing and come up with mitigations around that. We need to move on to our plan. So planning for inspection, maintenance, any repairs that might be likely throughout the life of the new pipeline. And then on to like work scopes and any monitoring and testing requirements. Implementation can be a challenge. So we plan, to have good procedures in place and competent people carrying out the work. So we shouldn't have any issues there. But if there are any issues that are found, this will be fed back into the beginning of the cycle so that everything has been well considered. So the new reservoir, it's a gas condensate reservoir. We think it's definitely economic to go after. You've got an opportunity there to increase your gas production by about 50%. So quite a considerable increase from where we are currently. We have 100 million cubic feet the platform produces. With a new reservoir, we have an opportunity for 50 million cubic feet extra. Like I say, the reservoir is 10 kilometers away, and others have suggested, studies have suggested that an 8-inch pipeline is going to be the best way to deal with this. I've got up on the right-hand side there, just known info, design, operating pressure, temperature. We've got CO2 and H2S, so this is a sour reservoir. And then we have our chloride and our bicarb content as well there. At the bottom, we've got the production profile for the for the 10-year period. And the main takeaway there is that in the first 2 years, we have basically zero water cut. So we shouldn't have too many corrosion issues in the first couple of years, but this increases up to about year 7 for it to peak and then drops off again toward the end. So the main challenges with this new pipeline is, like I say, it's a sour reservoir. So we've got 50 ppm with our operating pressure, it puts us into the sour service area. So that's going to increase our risk of all the kind of hydrogen damage mechanisms. So hydrogen cracking, stress-oriented hydrogen cracking, sulfide stress cracking, even embrittlement, blistering, all of that. And because of the kind of local and aggressive nature of some of these, you know, we could end up with a loss of containment, which obviously we have to avoid at all costs, really. So, you know, we've got particular areas where this would be a big problem. Could be inclusions in the metal if it's not sourced properly, manufactured properly. So we need to have a good selection of materials. Stress concentrations is another area. So any leftover residual stresses from forming, from manufacture, or from welding, they need to be really minimized to avoid these damage mechanisms. So the construction would be by a third party, but we would work with you guys to make sure that, that everything's being done as per procedure and everything's correct. We have just at the bottom there, I have a list there from cheapest to most expensive. We're planning to go down a chemical injection route to deal with on the internal side. So we think we could get away with a couple, but we would recommend going with an ACE carbon steel, just so you've got that backup in protection. From an external point of view, challenges are quite similar to most pipelines. So we would just recommend that we go with a kind of standard coating system and then backed up by sacrificial anodes kind of spaced along the line. So we've got a bit of a backup there as well in case anything goes wrong with the coating. So that's how we plan to transport the fluids back to the platform. Once they get there though, Solaire hasn't had any sour fluids to this point. So we have to think about what changes and modifications might be required from that side. So I'll pass you over to Austin, who's going to cover the top sides on Solaire.
Thank you, Stuart. So I'm here to talk about any modifications we're going to do to the assets in terms of the acid gas being tied back to the Solaire platform. So this is kind of like a P&ID we kind of drew from the list of equipment we got from the client to enable us visualize the whole process, see which areas are more at risk, which areas are less at risk, and maybe see any modifications we could do for it. So we might refer to this later on, or maybe if you have any questions regarding that. And then due to the new field, which is sour, which contains acid gas, your H2S and your CO2, we have done some risk assessment and looked at ways in which this new fluid being tied back into the platform is going to affect or cause any acid degradation. So possible corrosion or integrity risks are your sulfide stress corrosion, cracking, hydrogen-induced corrosion, top-of-the-line corrosion due to it being a condensate gas. And we basically want to manage this properly to affect any acid degradation or also to meet export conditions of the export pipeline. So these are some of the risks we've evaluated and we'll try to manage if we work with you guys, the contractor. So we'll move on to the major challenge for us in the sour fluid is the H2S, and we'll try to remove this, as I said, to meet export conditions and to avoid any integrity issues of, you know, some of these H2S mixing with water and, you know, affecting our flow lines or our equipment. So we'll try to remove this, and process of removing it is the gas sweetening. And we evaluated different factors to come about the best or two best methods to remove this H2S or acid gases. So we looked at the H2S concentration, OPEX, CAPEX requirement, because I'm sure it's important to the contractor and operator. We looked at other defined specifications of operating conditions, and we came up with two methods to sweeten our gas. Will be the regenerative, the amine contactor tower, and also the non-regenerative one, whereby we directly inject our transient into the flow lines or pipeline. So I'll move on to the next slide where I talk about or give you brief descriptions between the two and which is more feasible. So for the amine contactor, as you can see, it involves two towers. Basically, the first one is to scrub out the H2S when you put in your amine at the top, and it sweetens the gas. And then the second tower is basically to regenerate your amine, to basically remove the H2S from it. So that's the first one. It involves two towers, couple of pumps, couple of tanks, and so on. The second method basically is the direct injection, whereby you inject your triazine and it basically removes your H2S or your acid gases from the fluid stream. And for efficiency sake, we also have like an injection fluid atomizer for good contact and making sure that, you know, they mix with the fluid. We also look at communication with the chemical company to look at possible locations where we could inject this, could possibly be in the subsea manifold or other areas where we feel might be more effective to sweeten our gas and thereby remove the effect of it damaging equipment or flow lines. So these are also advantage, disadvantage, and we looked at, as I said, CapEx and OpEx. They all have their pros and cons and try to fit into the operator needs, the client, the contractor needs, and so on. And for the main takeaway from this is the contractor tower has a low OpEx because our mine is regenerative and the CapEx is a lot because you need those massive contractor towers and so on. For the direct injection method, it has a lower CapEx because you just need your pumps and so on. And then it has a high OpEx because you need to get loads of amount of your triazine because they're not regenerative. So when they are spent, you need to put in new ones. So these are the advantages, disadvantages for it. Due to time constraints, we can't go into much details for them. And then we looked at also the economics, which I'm sure is important to the contractor and also the client. And from what's initial assessments, which if we're working with you guys, we'll also look at ways to get a detailed view of this. This is just an illustrative view to give you guys an idea of, you know, the two processes. And from the look of it, the triazine direct injection method is cheaper compared to the contractor tower one. It's 3 million yearly compared to the 4 million yearly. These are just illustrative views, but we'll go into more detail when we have more details and more chemical compositions of the fluid and so on. So that's it for this slide. And then basically to summarize from any asset modifications, we feel or we recommend the triazine injection method to be the best for the solar platform, being that it's an existing facility. And, you know, having these contractor towers in the solar platform brings up to loads of issues whereby there are space constraints, there's also budget constraints and so on. So we feel the triazine direct injection method will be the best for this platform. And going forward, and due to our risk assessment, we've also done some risk analysis. We also try to make sure that there's material selection, you know, and it's NIST rated to MRO 175 to make sure that there are no any asset degradation and all our flow lines and equipment are good to go. We also look at fitness for service assessment to make sure that they last up to the estimated life of the asset 2032 or even more depending on the client needs. We will incorporate all of this in an operational way in terms of having a systematic approach to IOWs. We will develop, you know, strategy management document for management of change, risk registers, and so on. And make sure we've also evaluated that chemical injections have not been optimal in a way. We'll make sure that these are adequate and sufficient. Due to the condensate gas, we also see that there might be hydrate formation and then there might be need for hydrate inhibitors and so on. So these are the strategies we propose, and hopefully when we work with you guys, we'll dive more into detail with it. I'll pass on to my colleague who will conclude on our deliverable.
Thank you. Something else we would like to do is kind of our proposal would be looking to meet our net zero goals. You've got your 4 examples there. I'll go into more detail in the next slide. And just to kind of conclude where we are with our proposal is we start off with a full initial risk-based inspection just to clear up any assumptions. And then integrate this with the data management software, which would help us relieve any kind of potential risk from change. Again, we would implement these two with the operational windows, which again allow us to work our assets better, more optimal, which again would lead on to our net zero. And with our net zero, by having a more efficient plant, we will reduce our leaks, our methane leaks, which again will help our footprint, but also with less inspections, will be more efficient in that regard. So there'll be a smaller logistical footprint, again, helping meet our net zero goal, just trying to meet the industry's commitment to 50% by 2030. And in regards to the new field, what we would look to do is a direct injection. Again, with that, we would be using NACE-rated carbon steel just in the production of the pipe. But again, what we would like to do if we want a contract is work with the design contractor just to do a full economic study of this just before we made our final decision in this regards. And thank you for listening. That is us. And if you have any questions, we should be happy to answer them.
So, okay. Is it on? Oh, yeah, can you hear me? So just to summarize then, so you believe this is a feasible option for us to consider, and your selection for the pipeline is carbon steel with corrosion inhibitor injection. You didn't go into any details there. I don't know, maybe you could share your views around why that would be the most, considering the operational aspects of how this is going to be operated, why you think that's a good solution.
So yeah, so just a lot of it due to time, that we have basically a trade-off between CapEx and OpEx. So if we go for something fancier like a CRA clad pipeline, it's more expensive in the upfront. It would then be cheaper to run. So it depends a lot on the operator, on the client, what they prefer. Our suggestion was more based on the low upfront costs, and also combined with the fact that there's going to be, if we don't have the corrosion inhibitor, there might be more topside modifications that we have to go into. So, yeah, so for the 10-year life, we think that using the triazine injection and then just going with a cheaper material for the pipeline is a better option.
I think we believe as well with the new gas field will have increased revenue, so that will allow us to any higher OpEx costs from basically.
Hopefully that answers your question.
Thanks for the presentation. A question around data and data management. So there's lots of missing data. It's notoriously difficult to implement and populate an IDMS, a new tool. So what do you do with the existing inspection and corrosion management program?
Sorry, is that what would we do?
Yeah, do you keep running it? Do you abandon it? What do you do?
The plan would be to take all the data that is available and put that into the new system, so you can then have the history. You would then build on that, and even if you've got gaps in your information, it's better to have the information in there that you have available.
I think just to add, our software which we're offering you guys will have a synergy with your data manager, existing data management software, but we could retrieve some of this data, include them in our own data management software, and then have a record and history of them, whereby we can look for, we're not going to throw all your data. We just want to be like the assurance provider in terms of everything integrity related. We'll work with you guys and have everything in one place, whereby, because we had issues of getting some of this data back. So we want to make sure all this data with our data management software and the way we want to work with our IOWs, the way they're retrieved to your sensors and everything have been stored in one place. So I don't know if that answers, just add from what my colleague said.
Okay, so thank you. Another question to you. You talked about, you showed the risk matrix and I guess the key threats you identified as CUI, MIC, SCC and erosion, but you didn't really talk too much about mitigation and monitoring for those threats. So could you maybe talk around what you might do for MIC?
So for MIC, the way we look at it would include some biocides to mitigate and control some of this MIC, because from MIC we feel it's part of the fluid. So the best thing we could do, or the way we've looked at it from a high level point of view, is to have our biocide, incorporate our biocides into it. We also have our corrosion inhibitors and so on to work with the MIC to basically control our MIC. So I'm sure there will be other options. It depends on we working with the client and seeing what's best, what they've done previously, and then seeing how we can improve this issue for the MIC.
Sorry, just to add to that as well, we'd with the dead lag registers, we would also have them in place to kind of reduce, where possible, remove the dead lags from the system, and if not, they would need to be inspected, and ensuring our inspections, and there's sampling from the fluids and things as well.
Thank you very much. I was just wondering about did you look at the temperature gradients along the system, along the pipeline, how they might change over?
So we haven't done a detailed analysis of the temperature gradient, but just from kind of it starts off at 100 degrees and being at the bottom of the sea, it's going to drop down along the length of the pipeline. So, you know, your major issues would probably be at the early stages of the pipeline, and it would get less aggressive as the temperature goes down as we get closer to the platform. But no, we haven't done a full temperature profile of the pipeline.
And in terms of because you're using a carbon steel pipeline, obviously you'll be using the cathodic protection as you mentioned, but did you look at possibilities for design of that? Any more details?
Saying we've not done that, what we would look to do is maybe pass that to an actual DCP design specialist. I say what we were planning to do was do the full economic kind of survey into that before we made our final option, and then once we made our final option on the pipeline material, then it's something we can look to get a contractor in to do the CP design in regards to that.
Okay, thank you.
I noticed that in your 4 threats, you'd not identified external corrosion as a major threat. Have you got any comments on that? Was it?
So the 4 threats that were on the slide were the 4 key threats that we noted in the high and extreme. So external corrosion other than CUI was in the lower risk, but it was more in the medium and low risk areas on the matrix. So we felt the 4 that were shown on screen were kind of the ones that were most likely going to result in an LOPC or somewhere from the data.
And did you look at their history of failures, or was that not available to you?
Yes, so there's been histories of CUI failures and pitting, and where they've had to go in and do repairs from CUI and somewhere.
Yeah, in terms of the external failures, we think based on the data we've gotten, we feel because of the past operator have been using like a time-based inspection, time-based inspection strategy. We feel going through the main reason we feel is based on the time-based. So a couple of the assets haven't been inspected since when they were commissioned based on the brief we got. And we feel being is time-based, that's probably why some of this, they haven't been inspected. Some of the LOPCs we saw, we didn't see because like for the gas systems, for example, there were a couple of leaks, but then we feel if they were risk assessed and they were inspected, they will have picked some of these signs earlier on, even before some of these LOPs. I know you can't get everything, but some of these signs you could see them. So we feel going to the risk-based approach will risk assess everything of the platform and look at where those that have high risks. We'll also look at the historical failures and see how we can mitigate some of these, control them, and make the assets better for everyone. Yeah.
And as a result of this gas sweetening opportunity you're proposing here, does that introduce any new threats to this facility?
Anything you introduce into inputs, you also have problems output. So one key threat, for example, for the Transene is anything if the Transene is not spent, because we did a calculation, we spoke to our chemical company guys, and we did a calculation, and we felt based on precedent, based on any Transene that hasn't been spent or used up to remove it, could cause issues. They are hazardous and could cause issues down the line in the flow line or in the equipment. So we try to make sure when we do our calculations, make sure as much as possible all the Transene are used up, and then they don't cause any issues. For the condensate gas, being that it's a condensate gas, we also evaluate top of the line corrosion and so on. So these are things we've seen from a high level point of view to look at it, but once we get more data, more info, we can dive into this in more detail. Yeah.
Thank you. Okay, sorry.
Okay, Thank you very much, team one. Great job, well done.
Very nice interaction between you as well.
Thank you. Oh, thank you.
So there are some slides
Thank you.
at the front and then PhD and risk assessment at the back.
Okay, all right, thank you very much. Sorry, which team are you?
Number 3.
Number 3, all right. And did you have 4 people, and it's only 3 of you here today? Or
4 people?
Oh, you are?
Yeah, no,
I'm
so-
sorry, yes. Sorry. Yeah, I know.
Okay, can we ready? Yes, sorry, yeah, okay. Hello, we are team 3 of the Young Engineer Programme 2022. In our team, you've got myself, Matthew Drummond, you've got Vinuth Rajedran, Alessia Gutsell, and Cameron West at the end there. And our mentor was Bruce McKenzie over there. So this presentation is about the Solaire platform. The Solaire platform is currently 15 years old. As you can see in the presentation here, you have 2 fields, field Z and field Y. The field Z comes in on a 10-inch gas pipeline, and the field Y comes in on an 8-inch oil pipeline. They both run at a depth of 90 meters. And on the export pipelines, you've got the 18-inch gas line and the 16-inch oil line. There's also an opportunity to tie in a new field to this platform. So the agenda for this presentation, we're going to go through our risk assessment and what we found from that risk assessment. We're then going to go through our corrosion management program, so our mitigation controls and our corrosion controls to mitigate those, to manage those risks, sorry. And then we'll go through our material selection and our tiebacks, so how we intend to tie in the new fields to the current platform. So first off, on our risk assessment, we risk assessed all of the pressurized systems within the Solaire platform. This consisted of 108 lines in total. For the risk assessment, we used the Energy Institute guidelines. This here allowed us to assess 12 internal degradation mechanisms, as you can see on the board, as well as 5 external degradation mechanisms, again, also on the board. We used this risk matrix in the bottom right. This here, we first measured the likelihood on a scale between rare and highly likely. And then we measured the consequence based on a scale between minor and catastrophic. So for instance, if we had the oil pipeline and we assessed there was MIC in the oil pipeline, and we decided that it was highly likely that MIC would occur in that situation, you'd fall in the right-hand column here. Equally, after the consequence, if we decide the consequence of that failure would be catastrophic as a result of the safety, the production, and as well as the environmental impacts, then it would fall into the bottom right-hand corner here as you can see on this graph, making it an extreme risk. So for the purpose of this presentation, all we're going to cover are the extreme and high risks based in the D and E columns here. So what you'll see for the next few slides, they're all of the same format. At the top there, you've got the system that we're dealing with. So in this instance, we're in the gas system. You have the corrosion mechanism on the top right corner, so CO2. And on the left there, you see the red box. That indicates that in that part of the platform, you're going to have an extreme risk for this type of corrosion. In front of you, you have a fold out of the process flow diagram. You also have the complete layout of the risk assessment, as well as the block diagram, as you see here, which is in further detail. So for this system, we have a gas system, CO2 corrosion. We've deemed it to be extreme risk for the field Y wellheads and manifolds rises. Again, it's gas system, CUI on all of these points here. The red lines indicate the pipelines itself, which is the high pressure gas separator to the coolers, the inlets to the flash gas compression, and the outlets from the fuel gas treatment and distribution. Moving on, we have the atmospheric corrosion at these points. Again, you'll see it's only extreme risk that we found here, no high risks. Moving on now to the glycol system. We have crevice, CUI, and atmospheric corrosion all prevalent, and there's extreme risk in the glycol regen system. You'll find more detail about that again in the risk assessment in front of you. Next, we move on to the oil system, so the multi-phase system. You see here, we've got MIC, which is prevalent throughout the entirety of the platform. This is the worst case corrosion within for the whole platform. We have export oil pipeline is of particular requiring a particular attention as it has history of MIC and other corrosion mechanisms. We also expect to include a dead leg campaign for this particular corrosion type. Moving on again within the oil system, you have CO2 corrosion at these points. Preferential weld corrosion at these points, yellow boxes again denoting that it's high corrosion, red box is extreme, and in the produced water treatment with other slides again, you've got high and extreme risks both within those sections. You have erosion here for again the oil system, and erosion corrosion at similar points as a result of that erosion. So you have CUI at these points, extreme risk going into the high pressure separators, and high risk at the second stage and third stage separators. This doesn't look that bad, but actually when we went through the risk assessment, we found there were a number of unknowns on the platform, and these would be required to be assessed immediately. And Vinuth will cover this in further detail later in the presentation. Lastly, for the oil system, we have atmospheric corrosion at these points. Finally, for the risk assessment, we have the miscellaneous systems. So these are ones that just we couldn't fit onto the block diagram. We have contaminated water disposal, heating medium, relief systems, all with varying different corrosion mechanisms, and all again for the high and extreme risks only. So that concludes the risk assessment side of things. I'm now going to hand you over to my colleague Vinuth, who's going to cover the mitigation and corrosion control measures for those risks.
Thank you, Matthew. We have made a systematic investigation to identify the potential threats to the offshore platform facility. We identified around 10 corrosion types are having high and extreme risk, and 5 corrosion types are currently present in the facility. So we made a special strategy for each corrosion types to mitigate and control based on its risk level. The first one is MAC. Applying a biocides will kill the bacteria and mitigate the microbial activities. MAC corrosion controlled through the increasing the pigging frequency and MIC treatment with a different combination of biocides. And we use a single biocide, the bacteria will get immune and it will stay longer. So PWC and CO2 corrosions are mitigated and controlled with a selection of suitable material with resistance and applying an incubator and maintaining the incubator availability. H2S and erosion corrosions are mitigated with applying a H2S scavengers and oxygen scavengers and controlling the flow rate respectively. Erosion is mitigated with the do the sand flushing periodically and selection of the suitable material with high resistance. Galvanic corrosion is mitigated applying an incubator, or otherwise we can separate the 2 different materials with the separating layers such as rubber sheets or a coating. Crevice corrosion is mitigated where possible to do the welding and avoid the bolt joints. CUI is the hidden corrosion happen under the insulations, which will be mitigated and controlled applying a protective coating on the equipment and vapor barrier on the outer layer of the insulation, and choose the water resistant insulations. Controlling the vibration and pressure of the system will help to mitigate the fatigue and fatigue corrosions. Sometimes if we apply some absorbing layer on the equipment, which will help to mitigate the fatigue and fatigue without change anything in the operational conditions, such as rubber pads. So the final one is atmospheric corrosion. This will be mitigated and controlled applying a protective coating on the outer layer of the equipment and maintaining the coatings. I will go into the inspection frequencies further. So time-based inspection frequency starts from 3 months to 144 months with respect to the unknown condition to the low risk condition. As Matthew mentioned earlier, in these platform, number of equipments with the insulations are unknown. So that needs to be inspected within next amount of the time, and necessary action needs to be taken to mitigate and control the corrosion. As here, we want to add one more suggestion. If possible, we can avoid the insulation, so that will prevent the COI. Risk-based inspection frequencies are based on the inspection results, such as corrosion allowance or the wall thickness. Performance monitoring, visual inspection can be performed very often. It doesn't require any special arrangements. Close visual inspection, ultrasonic and radiographic testing, electrochemical technique needs to be done with the trained person with the appropriate time frequency. Advanced sensing technologies, bioprobe, corrosion radar sensor, and humidity sensor will help to monitor the remote area and confined area equipments continuously, and it can avoid the scaffolding and the other arrangements to do the remote area equipment inspection. For overall, we require biocides, incubator, coating, advanced inspection, and advanced sensing technology to do the corrosion management of this platform. And the overall strategy for this platform, we're proposing like preventive and predictive manner with the inspection and advanced sensing technology with the consumable materials. Thank you. I will hand over to Elisa for a new material selection. Thank
you. As part of the purchase of existing facilities, there is also an opportunity to develop another gas condensate reservoir 10 kilometers from the platform. I'd like to start with a brief introduction of data that we used as input to material selection of new pipeline. So initial studies show that 8-inch pipeline can be installed. Now you can see some important features of gas and water content at the top of this slide. We considered number of different materials options that can be grouped into 3 categories: carbon steel, clad or lined with CRA material or solid CRA. 2 steps have been taken to select appropriate material. First is corrosion assessment, and second is cost estimate. For the purposes of this presentation, we will only focus on CO2 and H2S corrosion. Let's start with CO2 straight away. So all materials shown here, except for carbon steel, are considered resistant to wet CO2 environment. And carbon steel requires special considerations. So why do we want carbon steel? Because it's widely available, it's cheap, and it's easy to weld, right? So when we started assessment of CO2 corrosion of carbon steel, we calculated uninhibited corrosion rate using NORSEC model. As you can see on this graph, corrosion rate turned to be quite high, up to 10 millimeters per year, depending on the temperature. Apologies. So we, just to highlight, our pipeline maximum operating temperature is 110 degrees C. However, since temperature profile is not known at this stage, we selected 60 degrees as the worst case scenario. What does it mean? We have to inject inhibitor if we would like to use carbon steel. So as the next step, we calculated corrosion allowance required if we inject inhibitor. You can see on the graph expected corrosion against years of service. Now, upper blue line shows 90% inhibitor availability, and lower green one shows 95%. There is also red 8 millimeter line, which serves as indicator above which you may want to start considering CRA materials. So as you can see here, 90% inhibitor availability will not really work in our case. So we should be really aiming for 95%. Now we know from the reports available for existing facilities that they couldn't quite meet 95%, unfortunately. So it means that specific spare and backup systems will be required to hit 95%. And the last point here, I would like to highlight, if we decide to prevent hydrates formation by insulating pipeline, then it will mean higher temperatures will be maintained along the pipeline length, and actually corrosion allowance will decrease. So that was CO2 corrosion, and now we can briefly move to H2S assessment. H2S assessment was based on ISO 15156. This graph on the left is specific to carbon steel. Horizontal axis shows H2S partial pressure. Vertical one is in situ pH. Based on our estimates, we will most probably end up in region 1. However, the safe way is to try and comply with region 3, which is the worst case scenario. It means that we shall use specific carbon steel grades and we should comply with certain hardness requirements. Now moving to CRA, same ISO standard, you can see 3 options as suitable for our conditions. Now 2 options marked with red cross seem to be unsuitable. However, we recommend that they're not completely disregarded because testing can be performed to confirm compliance to our project specific conditions. And lastly here, 13 chrome is not covered by this ISO standard. So again, further testing will be required to confirm suitability. That was corrosion assessment of different materials options for new pipeline. And now I'm going to hand over to Cameron, who will provide more details on material selection and modifications of existing facilities. Cameron.
Thank you, Lucia. So now that we know which materials we can use, we also need to consider the relative cost of each of these materials. And so in this plot, I've got the relative cost on the y-axis relative to carbon steel, and on the x-axis, we've got time. So as you can see at the time of installation on the left, we have carbon steel being the lowest price option for capital expenditure. But for this option, we need to further consider the requirements for corrosion inhibitor and biocide, which is why it slopes upwards. And so we may get a situation where a carbon steel clad or pure CRA option becomes the most viable option. Once we've chosen our pipe material, we need to make considerations for welding consumables. In general, the requirements for welding consumables is that we want the properties to match the mechanical properties to match that of the base material, whilst having a higher yield strength. And specific considerations need to be made for the presence of H2S as per ISO 15156 to limit or to control hardness and nickel content. Once we've selected an appropriate welding consumable, we'll need to test and qualify that it's compatible with the pipe material. To do so, we do the standard weld procedure qualification trials, including standard mechanical and chemical testing. And further to this, we may be required to do additional hardness, hydrogen-induced cracking, and stress corrosion cracking testing. Further to this, the production welds will be tested with at least 100% UT or radiography. Finally, in order to further investigation we've completed in order to assess the tieback opportunity is to assess the compatibility of the fluids coming in from the slightly sour field to the existing facilities on the Solera platform. In doing so, we've determined that there are a number of vessels and components on the platform which are incompatible with the new fluid, which specifically include stainless steel clad 316L vessels components. Likewise, there's a possibility that with the new fluid with high H2S and CO2 content, that we may exceed the gas export specification. And in order to mitigate this, we've proposed to, as you can see on the flow chart, to install a separate discrete first stage separation train for the new field with H2S scavenging by amine and a possibility of regeneration on that. This has a few specific advantages in that we lower the H2S and CO2 levels and stay within the gas export specification. We prevent the need to replace vessels existing on the platform and prevent any disruption and lost revenue this may cause. Yeah, thank you very much. And I'm going to pass back to Matthew to conclude.
Thank you, Cameron. So just to summarize, in our presentation, we have shown you the risk, the high and extreme risks of the platform, the Solera platform currently. We have also provided a corrosion management program that would mitigate and control those risks with appropriate strategies. Finally, we've then provided you with a number of options for materials to tie in the new field into the current platform, as well as a solution to manage the sour service that's on that platform. We are confident at this stage that with our corrosion management program, that it would mitigate and control the risks on this platform for the next 10 to make it last for the next 10 years. Thank you very much for listening. I'd like to invite my team back up just to answer any questions that you may now have. Yeah, that's good news.
You didn't conclude, so maybe I missed it, but you didn't, maybe you didn't mention which material you did prefer for the pipeline.
Yeah, we don't really want to insist on one material because it's always up to operator actually to decide, but we show that carbon steel is okay option, and normally people prefer to go for it. So it really depends on the strategy. If you don't want to invest a lot of money prior to the project, maybe go for carbon steel. If you want to consider overall cost, then other options may come into play. So it really depending on the strategy.
And if we'd selected carbon steel then, and you mentioned some monitoring, online monitoring there, but did you consider any sort of pigging activities we might have to do on that line?
Regarding pigging, Cameron, do you want to add something?
Yeah, I suppose we'd come from the design assumption that given that it's a subsea tieback, that regular inspection or clean pigging would be inappropriate, very, very high cost.
Yeah, but would we need to do it, do you think, on a carbon steel line?
Yes. Yes, we would need to do that.
Okay. Something to look into, whichever option we select.
Yeah.
Okay. Thank you.
Thank you.
Thanks for the presentation. One of your slides covered internal threats and then some of the barriers and mitigation options for the high and severe. But I guess there's a lot of threats and a lot of mitigations and a lot of barriers. So how would you prioritize where you're going to go first? I guess there's high and severe. There's a lot to do there. So what are you going to target? What would be a top two, for example?
Okay, so in the oil platform, line, sorry, you saw there that MIC was prevailing all the way through the line. So that would be one of our top places to go. Like I say, we would have a dead leg campaign. We would focus on the export pipeline for that as well, because it is prevalent there again. And that seemed to have the highest corrosion on per year. Vanessa, do you want to add anything to that? No, you want that?
Yeah, just to remind us that actually CUI can be an issue because there are a lot of unknowns on this platform. So we should really go and inspect, is there installation? There is no installation. So that is also like a big point and requires immediate attention.
Thank you. Just to follow up on CUI, so I guess inspection is one option. Did you consider the option of challenging the need for installation in the first place? Do you need it?
We did, and it's too bad that you already said that because we cannot show you that we did consider that. Yeah, exactly. Because sometimes, well, sorry, to my knowledge, that sometimes vessels can be, or pipework can be insulated so that people don't get burned, for example, and then you can avoid it by something else, not necessary insulation, like putting like a metallic cage around it or something so people cannot touch it. So yeah, we definitely considered challenging insulation.
Just to add one more thing. In some cases, they are adding for a sound control or the vibration control for some insulations. So that will be replaced with some other coatings available nowadays. I think that's weird. Thank you.
It's very comprehensive. Thank you. I assume that as part of it, you'd looked at, or did you look at the current sort of distribution of repairs and across the systems, what the current overall condition was? Yeah.
Yeah, so as part of our risk assessment, we had looked into where the areas of particular types of corrosion had occurred already. And we had factored that into what type of risk could be likelihood of failure we would have got from that. Where a particular corrosion mechanism had already taken place, it would already automatically gone to a D for that reason. So if we had experienced MIC, a likely from the likelihood section, if we had experienced MIC on the platform at least once, then it would be a D as a grading. If it was multiple times, it would be an E. If it was highly likely to occur that hadn't occurred already, we would put it as a C. And that would how it would become more likely to be needed inspected immediately. So that would reduce its inspection frequency.
Okay, thank you very much.
Did you consider the net zero emissions elements of this?
Yes, we did. Yeah. So this was part of our system to tie in the new platform. So instead of wasting the current vessels and pipes that were there, just changing them out, we thought adding a new system entirely would make it a bit greener. We also, as part of the, if you don't mind, sorry, but as part of the material analysis, it was also chosen to have instead of having the carbon steel, where you would have to change it out probably more frequently and it would become more costly, you have a material that's going to last a lot longer. Would you like to add anything to that? Sorry.
Well, just in material selection, I guess if operator would like to go for net zero, right? Is it called net zero? Sorry. They can choose solid CRA, so there are not so many corrosion products and no waste of material, you know. So that's one option. Of course, we can argue maybe you need to spend more energy producing CRA, but that's another discussion. So let's say if you want net zero, maybe let's go for solid CRAs for a new pipeline.
Thank you. Yeah, you didn't consider electrification or any of those sort of concepts?
No, not yet. We haven't.
Okay, no, that's fine. Yeah.
Sorry, yeah, I would just add to that. No, so we haven't done that yet, but this is just part of the preliminary assessment. So we would be considering that as a further investigation for this platform, providing, yeah, we were in charge.
Thank you. Yeah, just a question. Did all the analysis you've done, I understand the 10-year design life. Did you consider that perhaps the operator might want to continue beyond its design life, and what might the consequences be of your choices here or your proposals?
Yeah, for materials analysis, I think we mentioned that if design life is to be extended to 15 years, and if you go for carbon steel, it's very important to keep 95% inhibitor availability. It's like a must. Or you can actually consider solid CRAs or carbon steel clad with CRA materials, because then if you go for 15 years, like overall, like total price of the pipeline, maybe more or less equal for different options. So. We can take more. That's okay. Thank you.
Okay, thank you.
Yes, group 5. Yes. Team 5, yes. Team 5.
Yeah. Good evening. Just wanted to start off by thank you for taking the time tonight and giving us the opportunity to present our proposal to you. So we are Cairn Consultants, and we're just going to start off by introducing you to our team.
So I'm Jamie, my expertise in subsea pipeline design and integrity management. I'm Chris Slater, I'm a project engineer working in inspection at FPT.
Rosie Bird, integrity engineer for Golden Eagle platform.
And Lee Hunter, I'm an operations manager within Industrial Services. So our brief and the purpose of this presentation was to develop a corrosion management strategy, identifying how we'd manage the key risks and also maintain the current facilities on the asset. This was then followed by presenting a project proposal for a field tieback from a new reservoir. This then followed on to a sewer service analysis, which we finished off by carrying out a feasibility analysis, looking at the commercials and the operational impacts. And what you can see on the screen just now is a roadmap on how we got from project definition right through to the corrosion management.
So to determine the current integrity of the Solaire platform before the subsea tieback was considered, a risk-based assessment approach was conducted using the client's risk matrix and also in accordance with API 580. Each item has been risk assessed and the current internal and external condition reviewed per corrosion mechanism. We've pieced together a PFD and plotted on the risks of each item to be able to determine the current integrity and identify main threats in key areas holistically to the platform. The main threats are shown on the right-hand side of the screen. And as you can see here, we've got a lot of orange and red risk. This is primarily due to the known failures and anomalies, the harshness of the North Sea environment, and additionally, an applied level of conservatism, which has inflated the risk overall. So starting with the outside in, our main external threat is of corrosion under insulation. 25% of the items on the platform are unknown whether to be insulated or not. We recommend doing a line walk to get the insulation status reported and the condition of these unknown items. Next, we recommend applying a CUI strategy, such as this shown on the screen here, whereby the insulation removal dates are identified for high, medium, low risk items over the life of the asset. As you can see, our medium risk items are due this year. In addition, our high risk items were due to have insulation removed in 2019. So this is currently out of compliance. We had a glycol failure in 2020 and hadn't CUI strategy been applied and implemented, this could have potentially have been prevented. So we have high, medium risk items due this year for installation removal. So what we recommend is a thermography as a CUI screening tool initially to detect for water ingress and help prioritize installation removal. Here's a real life example of a success story where thermography is being used with a thermal image shown on the bottom there. And then a year later, when insulation was removed, CUI was detected. So, internal risks. CO2 corrosion has been noted on both oil and gas systems. Both oil and gas pipelines are inhibited. However, there's been note of failure, downtime of the gas inhibitor pump, which, as I say, has had significant downtime thus far and has reduced inhibition of this stream. We recommend inhibition of the separators to ensure carryover throughout the rest of the stream. Additionally, a review of the inhibitor to ensure it's water soluble is recommended. The corrosion rates are most prevalent at separation and diminished downstream. And moving on to the export system, what we recommend is dew point monitoring, and where there are prolonged periods of excursions, potentially insulating these items. Now, I know what you're thinking, mitigating against CO2 and introducing the potential of CUI. However, this would be managed through the CUI strategy. Next, we have MIC. So this is prevalent in primary separation, produced water, and the oil export streams. Raw seawater has been used to flush the separators, which is an accelerated area of introducing the bacteria within the system. So we recommend treating this seawater before flushing, or even better, utilizing thermography to detect solids within the separators and only flushing with treated seawater when absolutely necessary. We recommend a biocide kill dose followed up by routine biociding and sampling to ensure effectiveness. We have had a couple of repairs on the primary separators. We have 2 trains and 2 of the hydrocyclones have been replaced for an upgrade of material, so the critical path is retained. Vessel inspections is another high risk area. So what we recommend, we have a lot of vessels that have kind of limited history. So what we recommend is a risk-based inspection implementation to be able to determine and focus inspection on the high-risk areas initially. An example of this is the coalescer, where both internal and external risk and threats are simultaneously happening, with MIC noted in 2014, external corrosion the year later with a 1 mil corrosion allowance, and bring up to speed to date, we've now had a further 1.2 mil wall loss. So the written scheme of examination looks something like UT mapping to gain the remaining wall thickness, a fitness for service assessment, potentially a process review looking to downrate this vessel to allow repairs focusing on external first, and then an intrusive inspection to repair the glass flake lining when the shutdown permits. And then we would monitor this throughout life.
Okay, so the issue I'm going to talk to you about is the oil export pipeline. We've assessed this as one of the main risks for the field today. So we've had a few historical inline inspections, which we plotted here and used to predict the wall thickness through life. And we've also calculated the minimum allowable wall thickness based on DNV standards. So that's a conservative approach, because what we know about these defects is that they're localized in the bottom of the pipeline in the first 2 kilometers, and there's 9 of them altogether. As Rosie mentioned earlier, we've noted MIC and microbial activity upstream, so we suspect they're MIC, especially as we know corrosion inhibitor has been good in life for this pipeline. So the first thing we'd recommend is doing a more detailed defect assessment on these to tell you how far you can actually operate to with wall thickness. But the main thing we're noting right now is that it's probably very unlikely this pipeline will be able to operate all the way to 2032 based on its wall thickness. So our immediate mitigations would be implementing a monthly pigging regime to shore, reducing the water content from 2% right now to ideally 0.5, but 1% more, maybe more manageable, and also introducing biocide into the oil export system. So as noted, we don't think we'll be able to operate this pipeline for the rest of its life. So what we're recommending is a replacement strategy for the affected 2-kilometer section. So you can see here on the slide, the 2-kilometer area that's been affected. What we'd recommend doing is a temporary bypass utilizing a hot tap. What this will allow us to do is replace that 2-kilometer section with vessel intervention, allow us to maintain export around the bypass line while doing the replacement to reduce the impact on shutdown. This also has the good impact of reducing the cleaning requirements and pigging requirements prior to the replacement, reducing the impact in the onshore and the offshore facilities. So next I'll talk you through our approach to the new subsea tieback design. So we were asked here to look at material selection, welding consumables, and also corrosion mitigation. So we performed quite a conservative corrosion assessment. And what we found in this is we can reduce the through-life wall thickness loss to 2.5 millimeters using inhibitor, telling us that carbon steel is the feasible material, and that's what we're going to use. So looking a bit further into the material grade selection, we're in ISO 15156 region 1. So this allows us to choose a very high number of carbon steel grades. So we've chosen API 5L X65 due to the lower wall thickness requirements, and then the cheaper material requirements later on for that. And we verified this with wall thickness calculations. We're also choosing a CRA spool at the inlet. This will help us allow for a corrosion inhibitor mixing and also reduce the worst case corrosion rates at the inlet. Because we've got high temperature, high chlorides, and some H2S, we can't choose things like 316L. We did think about looking at a solid duplo. However, requirements for external corrosion protection, for cathodic protection, so we decided not to do that because of the cracking risk. So we've chosen Inconel 625 because the spool is only going to be of short length. So for welding consumables, we've been to specific manufacturers and suppliers, and we picked out 2 consumables we think would be perfect, both carbon steel and Inconel 625 if welding is required. So looking at mitigation of the internal corrosion, what we would do is, again, we've proven inhibitors feasible, so we'd choose that for internal corrosion mitigation. We would have that CRA spool at the inlet, and we'd also install an umbilical to allow for further chemical injection as required through life, for things like biocides and scavengers as needed. For external corrosion, we've done cathodic protection calculations to DNV standards and ISO standards. What this told us is we need 34 aluminium bracelet anodes on the whole pipeline to protect for corrosion through life. We've also chosen 3 LPP coating. This because it's got very good coating breakdown factors, and it's widely used in the North Sea. And we've chosen 2.8 mils of thickness based on ISO standards. So lastly, a few additional considerations we've looked at. And we have looked at reuse of the pipeline for carbon capture and storage. I'll get onto that more later. And we've done stability checks, reeling checks, and also some additional cost estimate just to tell us our design ideas are actually feasible.
So with the introduction of the new slightly sour well, we needed to assess what the H2S effect would be on topsides. So what we've done for this, if we have used ISO 15156 to essentially qualify the materials we have in topsides. Generally, we have compliance there, but there are a number of carbon steel products that require further qualification, but we don't foresee this to have any real issue. We do, however, have a CRA component that is 316L. That is a potential issue here. And this is due to the high chloride concentration, which kind of makes it susceptible to SCC. Of the topside components, there is two items that have the 316L as a material. That is the tube bundles of the first and second stage flash gas coolers. Therefore, we would recommend that these are changed out for a less susceptible material such as a duplex stainless steel. Overall, this is not the only issue we need to consider. We also need to consider the gas terminal entry specs, and for this we require further sour gas treatment. So after weighing up a few different kind of options, we have opted for a direct injection of a liquid scavenger, and this would be at the gas outlets of the separators. This is mainly feasible due to the relatively low concentration of H2S we have, and also the availability to retrofit to existing infrastructure. With the correct selection of the scavenging agent and dosing optimization, the products can be are biodegradable and could be disposed of along with the production water. So just to summarize a few of the management strategies that we have presented, we've highlighted 5 key high risk issues, which we've also kind of recommended remedial actions to either rectify or reduce the potential of failure. There are a number of inspection campaigns that can be implemented both topsides and subsea. This will not only help kind of gain the indication of what the current condition of the topsides are, but also help to build some historical data in order for further risk-based inspections or risk-based assessments to be carried out, and also optimize IOWs. There are a number of monitoring techniques that also could be put in place, the likes of at the erosion susceptible areas. There's currently daily UT checks being done, and this could be simply be changed out for a wireless monitoring system. Also to highlight some strategies to essentially increase the management of the facilities. For example, some anomaly procedures could be put in place to basically log anomalies and ensure they're closed out sufficiently.
To support all the technical work that we've done in the background, we also created a full detailed commercial model as part of our case study. What the image you can see there is a profit and loss analysis. So based on our analysis, we've projected that this venture could remain profitable right through to year 10. You can see in the cost section at the bottom there, there's quite a high spike in the year 1. The reason for that is that we've made the assumption that the full asset purchase costs and the cost of carrying out the field tieback project will be realised in year 1. In terms of the revenue, you can't see it there, but we've used to build our forecasted revenue, we've utilised the last 10-year average oil and gas prices just to give us some confidence in projecting future revenue. So those worked out at oil at $71 and gas at $4. And what we've also included in our cost there as well is we've made an allowance for an ABEX accrual, so that year on year the asset will build up a fund which can be used for either decommissioning activities or potential other investments, which Jamie will touch on after this. What our commercial model also allowed us to do is to just carry out a return on investment analysis, just to look at what is the feasibility of this. The blue line you can see there is a projected return on investment based on that model. The dotted lines you can see either side, we've just made up a best and worst case scenario, just allowing for plus or minus 20%, just to allow for any downturns or any upturns in terms of cost and revenue. The red line you can see at the bottom, we've put that in as to provide a bit of context. So that is simply taking the planned initial investment and then forecasting that based on if the money was in the bank on a standard 10% interest compounded over 10 years. So based on our return on investment analysis, you can see that even on our worst case scenario, it's still a significantly higher potential to have a much higher return on investment, which makes us confident in recommending this as something that yourselves and your clients should be looking at.
So the last thing we're going to discuss is basically, we believe there's a big opportunity here to reuse the facilities for carbon capture and storage. So this would primarily need to be assessed at the time. based on the current condition of the facilities, especially the pipelines, or the driving mechanics could be more things related to fracture mechanics and buckling. So we need to look at specific defects at the time for the pipelines. But this is an ongoing project here that's actually happening right now. And we think we've got a great opportunity with the Solaire facilities, because what we'd essentially do is, you can imagine this is the endurance reservoir, the Solaire platform would be here, and these future expansions are an example of where the tieback could be. So because the Solaire facilities have pipelines to shore, they're central in North Sea, there's a good opportunity to turn them into a CCUS hub. And that is something that, working with you, we could help deliver with the client, because we would recommend operating with this in mind for the future. So we also think there's a great chance here for this to look good on your client as well. If they're coming into the North Sea as a non-North Sea operator with this in mind, looking to help the UK achieve its net zero targets, I think this will be looked on very favorably. So overall, what we want to say in short is our solution can help mitigate the risk of the platform currently. We can work with you to operate through life and help manage the facilities in such a way that we look for future use opportunities. And we've shown with our cost model that we can do this profitability for your client. And thank you very much for listening. If you have any questions, they are encouraged.
Thank you very much. I'd just like to ask you a little bit more, explore a little bit more around your strategy for managing the H2S and this H2S scavenger injection.
Mm-hmm.
How have you considered the threats of H2S production on the materials that you've got, and how well you might be able? Did you look at how well the chemical inhibition program was running on the facility, and whether that was appropriate for the threats?
So the main thing we've done for that is taken the sort of worst case conditions we get from the new field tieback and then use that to screen what materials are going to be an issue. There were only a handful that were an issue, so 316L, 6 moly, and perhaps one other. The only ones that would be exposed to production fluids were the 316L. So the reason we decided to look at actually replacing those was because we just figured that we wanted to remove the risk completely. There are options to perhaps look at testing those materials further in the conditions for suitability of operating under sour conditions, but we decided just to remove the risk completely. Something we didn't particularly look at was the current feasibility of, we did look at also in having a H2S removal unit on the platform. We did also consider a higher impact things like amine units, but we decided they were too big. So H2S scavenger we chose because it was a lower impact, lower cost solution. And as Chris mentioned, because the field's only going to be producing for 10 years with the fluids sort of decreasing over that life, it's a more feasible solution to retrofit that, which is why we went for that solution.
And are there any downsides to it?
Yeah, there most likely will be downsides in terms of we can't ensure that that's going to be up and running all the time. We can't ensure that it's going to have 100% removal of all the H2S, but all we need to do is meet the gas export entry spec, especially. So that's one of the reasons we also decided to remove those materials. Takes away that threat of having to do an immediate shutdown should there be H2S in the system. So it's mainly just to meet that gas export entry spec. So yeah, there are some downsides to that.
Considered viable at terminal entries as well. So I think highlight correct selection of scavenger is also kind of dependent on aspect as well as kind of downstream. Kind of said that many of the byproducts are biodegradable, but I guess this is all kind of the active kind of feed stage. We're going to look at high level, but when it comes down to it, it's kind of weighing up with corrosion engineers and getting kind of a number of people to
Thank you.
Thanks again for a really interesting presentation. On the CUI strategy, so you talked about doing a line walk and then doing installation removal inspection.
Yeah.
Then what?
So, yeah, so basically, yeah, we would do the line walk, and we would also use the thermography as well to detect for areas of water ingress, as these are going to be our most susceptible areas. So once we've prioritized what needs to come off and streamline that across the kind of the field of life, yeah, we would just implement this year on year and utilize thermography as a yearly inspection to scan the insulated equipment.
Okay. Did you consider whether installation needs to go on? If it does, do you go like for like, or do you go for a different system?
Well, it depends. So thermography also has its downsides. So again, depending on the insulation type. So for example, stainless steel clad, you can't do thermography on these items. Can you repeat your question again? Sorry.
Yeah, so
Lost it a little bit
so
there.
once you've removed the installation and done the inspection,
Yeah.
did you consider whether that installation needs to go back on? If it does, would you use the same system? Would you put sensors underneath, or deploy some other kind of technology that would help?
So we would need the process engineer to really review, because we wouldn't want to upset them or the process. So yeah, we would need some input from them, whether insulation could be left off, remove the threat entirely. There are corrosion under insulation monitoring, like you say. We haven't really explored that option. I'm not familiar with it quite myself 100%, but I know that thermography is like tried and tested. I'm quite a big advocate for that.
I think our strategy would be focused on screening the high risk areas first and really trying to have a look at removing the insulation off and doing any repairs necessary. And then once we've dealt with the high risk areas that we know have CUI issues, we then look to implement that sort of thing.
Okay, thank you.
I was just wondering about the, you had a chart up of the MIC. Was that your calculated MIC rates?
So these are
Was it this one?
Yeah.
So these are the corrosion rates that were given to us initially, of initial observations. So yeah, that was just the information that was given to us.
What were they sort of general corrosion rates or specific to MIC, or?
Yeah, they're quite specific to the MIC, those corrosion rates. Yeah.
Okay. Just a question on the inspection side. Had you looked into NII, non-intrusive inspection type?
Yeah, so an NII inspections would be most favorable. Intrusive inspection, confined space entry, trying to avoid it if we can. So yeah, basically implementing NII within the written scheme of examination, within the risk-based assessment for all the equipment, especially honing in on these specific threats. Yeah, so radiography, if there is insulation there, and UT if it's uninsulated. And additionally, we would look to collate these inspections. So if we have CUI, and the insulation is being removed, we would look to obtain UT readings at the same time.
Okay, very good. Thank you.
So I was interested in your cost model. So I saw you considered the various different stages of life cycle costs. So just wondered if you'd considered whether we could extend this beyond the 10 years, what might be the consequences on the cost elements here, and what we might have to invest.
Yeah. So I think, as you can see, based on the current model, as you can see in year 10, the profit line on the graph, it does show that as we get to year 10, it does look like that is the optimum time to potentially be looking at alternative solutions. But part of the reason why we inputted the ABEX accrual into our cost model is we wanted to build up almost like a fund that can be, so build it up so with decommissioning in mind, but not being closed-minded to that, is building up a fund that can be used for alternative options, i.e. the carbon capture options. But yeah, that's definitely something I think that can be looked at. I think, as I say, the model was based on expecting the revenue to drop with reduction in production, but also expecting the cost, operational costs to remain very similar throughout the life cycle. As technology advances or and efficiencies advance, and as the operator becomes more efficient within the sector, because we've been quite conservative with the operating costs. We've went on the high side, knowing that the client is new to the asset. We're not expecting to be like an established operator that's got a lot of synergies and can really get their cost of a barrel down. So as I say, we have been very conservative, and I think that there's definitely scope that this could go beyond the year 10 life cycle.
Yeah. And did you consider those repairs that you suggested on the oil export line? They're included in.
The cost that we put down for the oil export was around about £20 million based on known projects that we've looked at in the past. So we did consider that. So yes, it's an expensive investment. However, we do feel if that oil export pipeline was to come out of use, you to feel the cost of production interruption is going to be a lot more significant than that. And this is a long-term repair. We did look at other repair options, such as pipeline repair clamps, because of the nature of the defects and that they're MIC. We don't know how they're going to grow specifically, and installing 9 repair clamps is a bit of a shorter term unknown solution. And we did look at a few other things as well, but we have factored that into this as well. Yes.
All right, thank you.
Any more?
Thank you.
Thank you.
Short break.
Hello and welcome everyone. Welcome to this presentation for the ICAR Young Engineers Programme 2022. We are Corio Corrosion Solutions, or Group 6. This is Aileen McDonald, Shravan Clare, and I'm Clay Cunningham. We also had Lewis Mann as a member, but he is in absentee today, but he was with us for the rest of the project. And our mentor was Dr. Mohammed down in the back. So why are we here today? We are here to present to you our corrosion management case study for the Solea platform with a slightly sour Newfield tie-in. What we're going to present to you today is a risk assessment. A process flow diagram followed by a risk assessment, then a tieback, and we have some sour service to go to today. And for that, I would like to pass on to Aileen, who will take your
So we started off with the scope of work provided by Bala Integrity by creating a PFD on the process conditions given. So as you can see here, we have highlighted all the anomaly observations provided to us by the contractor, and we can see that there's several anomalies across all different utilities. So we then put this into a table to go and categorise it into the different sections to then start on our risk assessment and give a starting point for that. So Shravan will take you through the risk assessment that we've done as a group.
Thanks, Aileen. So after developing our diagram, we have done a qualitative risk assessment for all the equipment. So here is the matrix, you can see it, and based on our qualitative risk assessment, we have classified equipment into 4 different classes: low, medium, high, and extreme. So for that, we need to have the likelihood on consequence severity. And for the likelihood, what we have done is based on our anomaly information. So we have used that and categorized again into rate to highly likely. And if there's no information available, so what we have done is we know the material and we know what's the fluid going through it. And based on the temperature and the conditions, whether there's a coating or not and insulate or not, and based on our experience and going through literature, so we have determined whether there is a likelihood like rare or highly likely. And regarding the consequence of failure, we have chosen failure consequence, namely on the safety, a personnel working near to the equipment, and otherwise if there is any disruption of production, and that leads to cost and also environmental impact. And what we have done is we have chosen a more conservative approach. So if the consequence of failure is higher for particular classification, so we use a higher one. So based on that, like for example, consequence of severity is like 4 and the likelihood is D, then it comes under extreme condition. And if that is the case, so that has to be attended very straightforward. Either the likelihood has to be reduced and or consequence of severity, and both would be really great. So So here is the one good example we are showing for the produced water section. So as an example, and here what we have understood is here you can see this corrosion mechanisms. There's several, but what the information what we have is that in these conditions, CO2 and MIC corrosion is more prevalent. So based on that, we have calculated CYF. So for all glass flake lined CS, we have got likelihood is significantly higher because there's a clear case, and because of the higher pressures and higher temperatures, and if there's a safety, it's very minimal. So we have put the risk category in the extreme conditions. And here you can clearly see one example regarding the poor corrosion management, which I'll be discussing in the coming slide. So here you can see there's 2011, there's extensive corrosion, they know it, but in 2014, there's a significant oily water leak and replace the carbon steel with DSS. So this is not really a good corrosion management program. And what we have observed is that over 80% of the topset facilities are in the extreme and the high category, so which is not acceptable. And this is based on the current inspection techniques currently forming. So what are the shortcomings is that they use the time-based inspection. So this is not right when you are looking into an extreme facility and also the low facility, wasting a lot of time and spending cost in low risk category equipment. And there's what we observe is that there is a poor administration of the inspection database as well, and there's a lack of inspection for so much of the equipment. So this result of this is a poor corrosion management, and the more corrosion in certain areas, and the significant leaks in the hydrocarbons. And there's a reactive management methods appeared, and we are looking into more proactive corrosion management of the assets. And with this, I'll forward to Ailey, who will go through the corrosion management things. Thank you.
Yeah, so with obviously everything that has been highlighted by Shravan, it was quite imperative for us to instead adopt a risk-based inspection programme rather than the time-based approach that is already in place. So I'll take you through this diagram, just as this will be our cyclical technique of risk management in a simplified version. So our first two steps here, the identification of safety issues and the assessment of safety issues, have been covered with what Shravan has mentioned, with our identification of the anomalies that have already been observed, and also obviously categorising all of the equipment on the top side in our unmitigated assessment. So part three of this is what we're interested in at the moment, which is the definition and programming of safety actions. So for us, we'll be trying to take a proactive approach in this, such as introducing barriers where they're not already in place. So this will be through such examples as picking correct coating solutions and making sure that they're correctly maintained. If there's any repairs or replacements involved, we'll be making sure that the material selection involved in these are correct for the fluids and the process conditions that they'll be facing, as well as chemical injection and biocide injection where necessary. I will also be doing this in conjunction with monitoring techniques such as ultrasonic testing, radiography, and such as like say corrosion radar in specific sections that we maybe see CUI. So then the fourth section here in the diagram, this would be on the client. We would expect to obviously implement our plan and follow up on what we have advised. And as I've said, this isn't just a linear approach. We would be doing this cyclically. This doesn't end just after we put this in place. This would need to get re-reviewed again and go back to stage one. Also, as we'd noted with the already in place plan, the inspection log was quite poor. The information that we were provided with was quite poor. So we'll be making sure that we create and use an appropriate data inspection database to officially capture any anomalies or observations and to ensure that management of change is followed correctly throughout. So again, this is just to show that we are following the HSE loop here, the diagram, and I've just explained it in a more simplified way with the diagram previously.
So going back to the example of the produced water system in place, this is again the unmitigated risks here. And as you can see here, from the mitigations that we are suggesting, such as inhibited injection, ultrasonic testing, inspection and maintenance of the coating systems with corrosion probes and microbial sampling, we can see that we have then decreased the likelihood of these events occurring. So as you can see, we haven't actually decreased the severity of any of these, as nothing has particularly changed, such as materials or anything, but more so with the inspection techniques and things that we are choosing at a more frequent rate, that our likelihood should hopefully then decrease for these to bring them into lower categories. So we performed this across all of the facilities, all of the equipment provided. And we went from our quite unmitigated graph here to much lower values. So in the original graph, we've seen that 80% of our assets were in the high to extreme categories, whereas now we can see that 80% is in the low and medium categories, with only 2% in the extreme. So from this and the new ratings and the reassessment, we have then now implemented a new inspection plan, as we can see down below. So example for low, we'll be looking at this to be inspected at a minimum of a 60-month, medium for 36, high 24 months, and extreme cases should be monitored at a minimum of a year apart from each other. So as part of the scope given to us by BALA Integrity, we also were given this new gas condensate subsea tieback. So we've just produced a diagram here just for illustrative purposes only, so we can see our new gas condensate line, our existing infrastructure, as well as our export from the Solaire platform. So we were given the data that there would be 50 parts per million H2S, as well as 2.2% CO2 content. So with this, we then calculated partial pressures of 1.225 and 539 kilopascals of H2S and CO2 respectively, based on the design pressure of 245 bar. So when we add these together using ISO 15156, we then came with a pH of 3.7, which then had us landed in the sour region 2, which meant that this would be a medium sour, and we would have to then assess this for our material selection. The ratio, the partial pressure ratio of CO2 to H2S was 440 to 1, which meant that it was in the mixed corrosion regime, but predominantly CO2. So we took this into account when we used electronic corrosion engineer software corroborated by NORSOC M506 to calculate our corrosion allowance to be 2.82 over our 10-year lifespan. So we can see that in the table here to your left. We can see that our corrosion rates between year 1 and year 3 are higher than the rest. This is because we don't have any water running through, so no bicarbonates, which meant that this wasn't a buffer, so it was a slightly higher pH. So our pH does lower in years 4 onwards. We also then calculated an inhibited rate of using NORSOC M001 to give us a corrosion allowance of 1.18. So this meant, because we had a relatively low corrosion allowance, we could then select a seamless X65 carbon steel sour grade material for our line pipe. And we had to be wary of the potential corrosion and types that we would potentially face, such as CO2, H2S, top of line, bottom of line, microbial induced corrosion, erosion, and preferential weld corrosion. So we've got measures in place to mitigate against these, such as the injection of corrosion inhibitor, scale inhibitor, and MEG to prevent hydrates into the field periodically when required, when we have more information to set up a regime on this. We'll also be making sure that the well consumables are compatible with the material that we have selected, and ensure that it is also sour grade.
For the external corrosion, we decided to select a 3-layer polypropylene anti-corrosion coating. This was due to the maximum operating temperature being 110, which was in the range for 3-layer polypropylene, but not other coating systems such as FBE. We also have performed a preliminary cathodic protection design, and aluminium zinc indium bracelet anodes shall be welded to anode pads along the length of the pipeline at approximately 300-meter increments. And also just a note here, just to ensure that BALA Integrity is aware that we have not considered existing subsea infrastructure in this design. So because we have now injecting a sour service, a slightly sour line into our topside facilities, we had to then perform a sour service assessment of the platform facilities, which Craig will take you through now.
So, the sour service, obviously the presence of H2S. This is obviously just our original PDF. And here you can see we have the new field inlet and we have the processing there. So for sour service, you would expect things along the lines of hydrogen-induced corrosion, stress corrosion cracking, acid corrosion, and microbial. So with that in mind, this would be similar to CO2. So we took the data from the original field and we took the data from the other field, the new field, and did some calculations of their pH, and we have taken it as 1/3 stream, 1/3 of the new stream to be from the new field and 2/3 from the existing. The new field had originally 50 ppm hydrogen sulfide and 2.2% carbon dioxide. When you combine the streams, you end up with 1.4% CO2 and 16% part per million for H2S. This is not in the sour region. There we go, the blue dot. But we took the extreme of this from the wet processing equipment at 76 bar to give us the highest input. So the whole system is not sour as far as we can make. The inputs into the first stage gas separator is dry gas, so there's no need to consider this kind of corrosion in this situation. And similarly, after the glycol contactor, there's no oil, H2S in the oil. So again, nothing to be concerned about. Our intentions are to do biocide treated seawater injection rather than produced water injection. And for our material selection, we were using NACE MR0175 and ISO 15156 for corrosion resistant, corrosion grade steels. We'd also have to consider corrosion grade fittings and fixtures, washers and the likes. But with this not being a sour region, we would not need to do any serious changes to the existing platform, and therefore any other study would be in the future. And I'll pass on to Sharon.
Thanks, Greg. So this is our summary. So unmitigated risk assessment and currently implemented time-based assessment. So I created almost 80% of the equipment in the high and extreme. And after our integrity management plan using a risk-based inspection methodology and being more proactive, corrosion management is adapted rather than reactive methods, and it decreased the risk almost high and extreme, almost from 80% to less than 20%. So from the new tieback new field in sour region 2 based on ISO 15156, and we have few recommendations here, having a seamless X65 carbon steel sour grade and 3 mm corrosion element selected, and we need to have compatible well consumables. and the coatings selected, that is like 3LPP. And regarding the bracelets, aluminum, zinc, indium anodes need to be selected. And for corrosion inhibitors and MEG are recommended. And assessment regarding the already existing one. So what we have observed is that commingled gas inlet had a CO2 of 1.4% and H2S of 16 ppm. So assessment revealed that they are suitable for processing the new field conditions. However, we are capable to do more SOAR assessment. And finally, what we would like to say is we are more capable and also more passionate and professional team, and with a diverse background, and with the sole aim of developing designing corrosion management program to decrease the cost and successful running of the plant for the industries. And we look forward to working with you. Thank you.
Thank you.
So I noticed on your PFD, when you'd identified the current threats, you'd identified that the oil pipeline had some challenges. Did you consider that any further in your?
Sorry, is this the 16-inch oil export line?
Yeah.
Yes, so in the information provided, we had seen that there was wall thickness measurements taken where there was quite a bit of degradation, it had seemed. So this had actually stayed in our extreme category when we'd done the risk assessment. This was one of the very minimal parts that did stay in the 2%.
Thank you. And just on your conclusion that carbon steel was appropriate with corrosion inhibition, did you do any further calculations on availability requirements of the corrosion inhibitor?
Yeah, so when we done the corrosion inhibitor, we assumed availability of 90%. And we had used M001, NORSOC M001 to calculate the inhibited corrosion rate.
And did you consider how well the facility had been managing its chemical injection and whether that 90% might be achievable?
So this isn't something that we had actually considered in great detail, to be quite honest, but also it's good to bear in mind that we had a relatively low corrosion allowance to begin with at 2.82 millimeters across the 10-year lifespan, which, yeah, I suppose some you can get quite significantly higher corrosion rates than this. So we could then reassess this again. But it seemed relatively low to begin with before the inhibitor was added.
Thank you.
Thank you. Well done for presenting as a 3 rather than a 4. Not
Thank
easy. A question. One of the I think there's a risk matrix summary table you had. After the mitigations, it showed that the number of extreme items had dropped, but you'd also extended the inspection frequency as well. Can you say a bit more about that, please?
Sorry, what do you mean by extended the risk frequency?
I think you had your 12 months, and you talk about a shorter interval as earlier on before the mitigations, and then you extended it after.
Yes, so sorry, this was the shorter intervals afterwards, was the 12 months afterwards, because it had seemed beforehand there was really quite limited inspection going on before this. Sorry, that was probably just myself, a lack of clarity there.
Thank you. Where's my other question?
Thank you very much. Just wondering, in the last section of presentation, you looked at, you just assumed, I believe, that the new tieback would operate continuously. Yeah.
Yes, that was our assumption.
So, so I guess you would need to extend that to look at different scenarios, perhaps, when it wasn't, when it was off and stuff like that.
Yeah, so I think we'd based our sour service assessment on year 1, which was the highest production rate, which would then mean that would be the highest H2S content when commingled with the existing field. But yes, you're right that we would maybe have to then consider if the if the new fields, do you mean if the old fields was then perhaps treated as new field for the H2S sour service assessment?
Yeah, I just wondered if you'd widen it out to look at all the different scenarios of different inputs. Yeah. But,
we'd done a quick assessment on if the old field wasn't was effectively shut off, and it was only the new field, because then that would bring our H2S partial pressure back up to 50 parts per million. But then again, because it was at 76 bar was the highest pressure equipment that we had, it still didn't really have much cause for concern at these pressures. The partial pressure was still relatively low.
Okay, thank you.
Thank you.
Just going back to, I think you identified in your risk assessment that the utilities was one of the high risk areas. Was there particular utilities that you felt were a high risk amongst that?
From memory, from the utilities, we had a few issues with the diesel and fuel gas, and there also did seem to be mostly issues in the gas utilities, I would say. So we would have to then obviously take these into consideration extensively when implementing our plan.
Thank you.
I had a question on some of the threats. You talked at length around H2S and CO2 and MIC. I think erosion is another issue that we've flagged. So can you talk something about what you do to mitigate and manage erosion as a threat?
Oh, for mitigation, erosion corrosion. So one thing is processing. For example, if you have a cleaning of processing of the seawater containing the solids, so filtering prior to it, that's one of the ways. And other one is having the erosion resistant materials.
So yeah, I noticed that you focused on your reduction in risk and that was obviously driving your inspection intervals. I think I saw the maximum there was 5 years. And it seemed to take, the risk was greatly reduced, I would say, looking at what you proposed there. Had you considered, and you were considering there were a number of mitigations that you mentioned, had you taken into consideration any confidence in those mitigation measures, and how might you iterate that if something wasn't as good as you'd expected?
Regarding
Yeah, so I think we have then taken these into account regarding the AP 5.1. But again, we've done this under the assumption that the client will actually follow our plan and our techniques. So if there was any issues with this, we would have to obviously get in, together with Bala Integrity and Capercaillie to refine this further if there's anything that they want to look at and maybe don't think that's correct. So I think that would maybe cause further discussion with the client themselves as well.
Okay, thank you. Thank you.
Oh yeah.
just. Good evening, everyone, and welcome to our presentation. My name is Chris Hines. I'm and we're here to present to you our proposed strategy for the integrity management of the Solera platform.
Team 4?
Yes, team 2.
Oh, team 2.
So here we've just got a brief overview of what we're to cover today. As you can see, our risk assessment has been split into 2 categories: with presentation, process, and utilities. The risk assessment was carried out using the methodology given to us in the documentation at the start of this thing. So the main principle, which our strategy is based on, is continuous improvement, as shown here by the Plan, Do, Check, Act cycle, with all of our strategies following this process as referenced in pages 265. I'm going to pass you over to Lewis, who's going to cover the process side of the risk assessment. So, as you can see on the screen here, about 61% of the equipment in the process side falls into the extreme or high risk category. A lack of inspection data has been driving a large proportion of this risk. We believe once we get involved with the asset and instigate our inspection plan, which hopes some of those risks could come down. But as you can see on the screen, the main threats internally, we've got preferential well corrosion, erosion, CO2, and H2S pitting. And along with MIC, which we see as a key threat. And in the terms of the H2S pitting, we see this as definitely something to look further into, especially with tying into the sour gas. Externally, we've got the threats of chloride pitting, stress corrosion cracking, atmospheric corrosion, galvanic corrosion, and CUI, which is a bit of a theme across the asset, which Chris is going to go into a lot more detail on later. So how are we going to manage these threats? So referring to DMV G101, we've identified inspection activities both internally and externally to start doing with our inspection plan. So internally, in terms of preferential weld corrosion, we believe installation of continuous UT monitoring probes would help here. This along with inspection activities on the hot spots such as UT, RT, and phase array and long range UT. On the MIC threats, we believe a full chemical review is required to understand why the biociding is not acting as we'd like it to, whether we require some further chemical injection or what needs to change there. In terms of the erosion, we believe we need to have some conversations with process engineers to understand whether we can modify the flow rates in places to minimize that threat going forward. Externally, we've got similar inspection activities, but on the CUI, we recommend radiography along with close visual inspection following de-insulation or penetration testing if we don't remove insulation there. Other threats externally, we've got the chloride pitting. We believe discussions with the instrumentation engineers to discover if we can lower the operating temperature going forward, and that should also reduce the OPEX. And also for the stress corrosion cracking, we believe some chloride monitoring is required. In terms of the galvanic corrosion, we believe inspection of the current coatings in place and to determine if there's sufficient material selection right now. So moving on to the utilities, our risk assessment has noted approximately 50% of the equipment as categorized as high to extreme. Once again, a lack of inspection data has forced us to be more conservative with our RBA. Once additional data has been gathered, this will be updated and reviewed as per the Plan, Do, Check, Act cycle earlier. In addition, some lower risk equipment could be potential candidates for event-driven inspection once confidence has been gained, which we feel can add real value. In terms of main threats, internally, we're seeing a continued MIC presence throughout the utility system as well as the process. We've also got the potential for acid corrosion within the glycol system. There was a glycol leak in 2020. At the time, this was attributed to CUI. Based on the fluid and the rich glycol pipework, acid corrosion is expected. However, inspection data in this area is limited. We also have the threat of O2 corrosion, most notably in heating and cooling mediums. Once again, this is expected based on the fluid. Again, inspection data has been sparse in this area. And internally, we're looking at pitting and cracking presence throughout the CRA locations, with several instances where the operating temperature is on or above the pitting and cracking thresholds for these materials.
As previously stated by Lewis, CUI is a massive issue on this asset, which I'm going to cover in just a bit. And finally, a general external threat similar to the process side. So how do we plan to manage these? In addition to inspection techniques used here RAD, we also plan to conduct a full chemical review, stated by Lewis. This review will determine whether current biociding is sufficient and if pH levels have been maintained to prevent acid formation within the system. In addition to this review, we also recommend looking at process control, in particular flow rate. This, combined with an updated deadline strategy, we feel will dramatically reduce the threat of MIC. For the heating and cooling regions, we suggest monitoring to determine whether oxygen is present. If high levels can be found, then this should be part of the wider chemical review. For external, we feel a renewed focus on hotspots is advised for dealing with CVIs. Obviously, 100% CVIs are expected, but in making sure extra attention is paid to these hotspots will ensure anything that's identified and managed. For the CRM locations, we recommend looking at process control first to see if the CRA equipment can operate at a lower temperature and still operate as desired. If that is not possible, thermal paint may be the best option moving forward to keep pitting and cracking at a minimum. Finally, we also suggest some proactive fabric maintenance to combat general external threat. Again, this is something we feel can have real value for your client. So, as I previously said, CUI is a major problem on this asset, and during our risk assessment, we noted a major concern. This graph shows us the insulation status for all of the equipment contained in the risk assessment. As we can see, 56% is not insulated and therefore not a problem for CUI. 21% is insulated and therefore a risk. However, we currently do not know the condition of the insulation, apart from very sparse inspection data and anomaly reports. What concerns us the most is the 23% where the equipment status is unknown, the insulation status is unknown. If you do not know the status of your insulation, you cannot possibly identify CUI as a threat. This problem is compounded further when you look at it via system. Now, as you can see, this unknown status is not present everywhere, but it is considerable in a couple of systems, most notably the oil processing. As you can see, 15% is currently susceptible to CUI. However, 75% of the equipment is currently unknown, creating a massive blind spot for us in, if not the most important process system. Another note of concern is the fuel gas system. Again, high risk, but with 40% of your system known as a blind spot. Incidentally, this is also the system where in 2021, there was a 70 kilo gas leak, which resulted in the platform shutdown, and CUI was noted as the cause at the time. It's also worth pointing out that the current insulation status of that pipework that failed is unknown. Now, as we're well aware, CUI is one of the major threats facing the oil and gas industry. In the North Sea alone, many assets of which are now operating beyond their expected design life, 60% of pipe failures are being caused by CUI. As a result, the HSE has been fairly aggressive in warning against CUI, for example, in Directives KP3 and KP4. However, the current lack of predictability can cause hesitation and a fairly heavy-handed approach, restricting lots of insulation at a significant investment for potentially little reward to CUI is not found. So, how do we deal with this? 2 steps. First is identifying and managing current risks. It's essential for us to understand the full CUI risk on this asset. Our plan is to carry out a one-off campaign to gather relevant information to create an insulation CUI register. This register will be the foundation of any CUI work going forward and will work alongside your client's current anomaly management system. This campaign will aim to capture the information highlighted in red here for all equipment with an insulation status of yes or unknown. The second step is mitigating long-term threats. Our plan here is to communicate and work with your client's process engineers to review the need for insulation based on operational requirements. This should give your client the information they need to begin a targeted insulation stripping campaign. Now, the scope of this campaign can vary depending on the resources allocated. You could look at hydrocarbon vessel and pipework,
focusing on vulnerable equipment that operates within the current optimal CUI temperature range, or you can look at where CUI is already been established. These are just a couple of the options that could be available to you. And finally, insulation retention will also form part of the early work of this contract. Again, working with your plant process engineers, ensuring that insulation does not have to be prematurely removed will significantly reduce the cost of any CUI campaign.
So as we've been made aware, the client is looking at the potential of tying in a sour gas reservoir into the current Solaire platform. So what are the main risks facing this and how do we intend to manage them? So the existing topsides and subsea piping materials have not previously had to deal with this kind of sour gas. So the main question is whether the current materials are suitable as per NACE MRO 175. As you see on the screen, there's only one piece of equipment and material that we really feel is a concern at the moment, which is the carbon steel. We don't know the exact grades being used, so we don't know whether it fits in. It is one of the resilient materials, sorry, it's in the 175. So we do believe some material testing is required on these to be sure. So short-term mitigations, should we tie in this sour gas, would be to have an inspection to understand the true severity of the sourness, but would recommend a full chemical analysis to understand the full threats being caused to the overall platform should we tie in the sour gas. Along with this, we would recommend a supplemental MBT, which we'll go into a lot more detail on in our inspection plan separately. So one of our main priorities at the start is the H2S and CO2 levels due to the gas terminal restrictions. So our initial mitigations we'd recommend would be installation of a corrosion inhibitor, a scale inhibitor, and a H2S scavenger. And this will hopefully bring some of the key threats down. However, if we still feel there's key threats there, we would have to look at a strategic change out of materials. But this is obviously a much more costly process and one we would like to avoid if we can. Regardless of what we put in, once we get the inhibitors and such in, we recommend regular testing on these to understand the performance, especially as they've had less than optimal performance in the past. So should we tie in the new reservoir? What would we recommend for the pipeline? So it's essential we pick the right material, but we also feel the low cost would be a key driver for yourselves and your client. So for this reason, we'd recommend carbon steel, matching the 8.2 requirements in 175, with the grade shown here in bold on the screen. Whatever specific grade is decided on, we would recommend they undergo hardness testing to understand if they're definitely resistant to HIC or SWC. But according to the 0175, they're generally resistant at that hardness. Welding materials we would use, we recommend carbon steel welds, but these undergoing hardness surveys to understand if they're at the correct hardness levels and are more resilient to the risks. And we recommend low percentage hydrogen consumables are used to prevent introducing further hydrogen into the risk. So the main benefit of these materials is a lower cost, and they are mostly resilient to any of the threats coming in. There are other exceptional materials such as DSS 22CR, but with this being a more expensive price point, we believe carbon steel is the best choice for this. Hand over to Chris.
So one of the steps in carrying out threat assessment is to identify possible damage mechanism through the RBA process. And this flow diagram further illustrates the credible damage mechanism identified on the oil system. So we considered both internal and external threats, and also we considered the corrosion barrier and the operational barrier. And we make sure that we use consistent and systematic approach throughout the system. Here's another example where we take into account material selection for the produced water system, where almost 80% of the component were constructed either from duplex stainless steel or carbon steel with glass plate. And here is for the threat, the top threat identified on the gas system, where it's further to the gas dehydration process, where it is expected to be dry gas before get exported through the pipeline. And another example where you consider the threats on the glycol system and the operational barriers. So this 12-year look-ahead table provides an overview of the risk-based inspection plans for the facilities very high and high criticality items. And also the task count on column H, column R, and the duration on column S. So once we get the task count, then we can estimate the duration using the inspection norms. And then from there, we could estimate what are the total inspection hours. And this is the 12-year look-ahead plan for all the RBI plans established for the facilities medium and low criticality items, where we plan to inspect from the second year onwards. So all very high and high criticality items are planned to be inspected during the first year using NDE or IBI during turnaround or at the earliest available opportunity, and all the medium and low criticality items from the second year onwards. So once we have the estimates of the total hours using the inspection norm, then we can calculate the cost for the inspection activities. As you can see here, the differential rate between the advanced NDT and the conventional NDT compared to the day rates. And on the table here is the estimated cost for the integrity support, where the onshore and the offshore integrity teams shall provide support in all aspects that includes corrosion management, anomaly management, planning, and IDMS support. And the last table on the right here is the estimated cost for the equipment, which averaging at about 118,000 pounds per year. So based on the estimated cost on the previous slide, we then now get to see what the total cost would be like. The annual cost would be somewhere around 966,000 pounds per year and around 11.6 million pounds for the 12-year period. If we factor in the 2% inflation rate every year, we would be looking at a cost around 13 million pounds for the 12-year period, which averaging at about 1.08 million per year. Please note that RBA is a dynamic process, and meaning it could change based on the new information received. So this table and estimate should be used as the guidelines. And then we move on to the corrosion control matrices developed for this facility. As an example, this table below represents a snapshot of the master CCM that developed by our team. As you can see from the table covers the management of corrosion through chemical, design control, and the operational control, and also the target parameters for the chemical management. And this brings us to the last question, where the most important question, why us? We understand the challenge and the issue faced by the upstream oil and gas industry. And our team brings new ideas, measures for your asset. We use consistent and robust approach, and most importantly, remaining compliant.
We're determined to challenge status quo, while at the same time able to offer alternatives which are digitally supported and cost effective. The good integrity plan implemented, not only will we be more efficient, we can eliminate major incidents and reduce the amount of fuels and emissions, which will contribute towards the UK oil and gas net zero targets.
That's why, ladies and gentlemen, we feel we are the best choice for your client's asset integrity and corrosion management provider. Thank you for listening today. Do you have any questions for us?
So hello. So I have a question around your selection of carbon steel for the new pipeline. How did you assess? How did you go about deciding that carbon steel was the right material there?
So looking at the main things we looked at really was NACE 0175 and sort of looked at the different options within that, which were most resilient, but we really managed the most cost effective approach. We just sort of looking at what could fit in, what was resilient to the threats, which carbon steel was the best that would be at that lower cost area.
And how did you look at how did you consider it was resilient to the threats?
Well, it's mainly due to it being stated in the standard that these grades are at the correct hardness levels, so they're more resilient to it.
Okay. Okay, thank you.
Hi there. Thanks again for a good presentation. And again, a team of 3 instead of a team of 4. So that's not easy. So well done. On the CUI, you talked about, I think it was 20. I can't remember my writing. 23% of the systems didn't know if you had any insulation at all. And then you gave a very detailed 12-year look ahead on inspection, planning, resources. But I guess you've got a lot of unknowns at the start. So how are you going to adjust that plan with what you don't know yet, and then I guess risk assess what's going to have to shift?
So kind of what we said, the first step is fully understanding the CUI, full extent of the CUI risk. Once we carry out that campaign, which will have a one-off cost, it will have to change. The RBI will be viewed as an iterative process, and then it will get factored in. If there are immediate threats that we find from that one-off campaign, then they will have to be managed on a case-by-case basis, whether going through an anomaly system or if they can wait until a stripping campaign can potentially mitigate the long-term issues that it may find.
Okay, thank you. And I guess a follow-up, again, so lots of detailed costings on resource, equipment, planning, etc. But I guess what's your view on, again, you talked about deploying lots of barriers at the start. So how does barrier deployment and barrier effectiveness have an impact on your long-term inspection plans?
Thank you for the question. Well, I believe the most important thing is to really understand what is the actual condition at the moment. Well, the data given to us, it's maybe we need further detail on that. Just want to take one statement that I read from UKHSC, one of the good practice document, say about aging. What define aging asset by UKHSC? It's not about how old the system is, but about how much you know about your system, its condition, and how it change over time. So we need to first know what are the conditions first, and just based that kind of bring us to find out which one is the highest criticality, and then plan for the first year which one we need to attack first and know what are the condition. And then from there, we could do the updates on the RBA base, and also need to know what about the status on the chemical program as well.
Able to answer that. So it's kind of clear from the data that we've received and what we have found that the previous ownership and stewardship of this asset has not been up to standard. It's not been acceptable. And part of our job with your client is helping them regain confidence in the asset. Particularly that first year of inspection is significant, and that 12-year plan will definitely change based on what we find. But we feel that the knowledge and the skill we have in our team, we are in the best position to do that for your client and help your client achieve its goals.
Thank you very much. On the subject of the CUI again, in terms of the perhaps compiling a CUI register, what would you see as the main checkpoints for completing that?
For me, so all of the points that we have in red there, is the installation present, is the non-negotiable, full or partial? That is nice to have, yes, but as long as we're aware that there is insulation present is the main thing. The condition is vital. Is it being properly maintained? Is there patches? But also a key one for me and for us is the location and the insights we can derive from that. The location of the installation on the platform will be vital in kind of determining if CUI is going to be a threat. Is it exposed quite heavily to the marine atmosphere? Is it under deluge systems? Is it inside? And is there proper ventilation? Or is it in a situation where moisture can build up around the insulation? Those points I feel are all valid and all critical. However, there may be other ones when we start the campaign that we realize actually there are a couple of extra points that we need to, data points we need to gather.
I think you had about 15 different systems that you mentioned earlier on in the slides, but what did you check how many of those were in cyclic operation, intermittent or aspects service?
That's not something I don't know if the information that we had. Yeah. No, that would be something we would have to check, but we'd be happy to get back to you on that with the correct answer.
Okay, thank you.
Yeah, 4 of us.
Yeah, right.
Good evening.
Sorry. Which team are you?
We're group 6.
6.
Yes. Sorry, group 4. We're 6. Yeah. Yeah, 6 to go for group 4. Yeah. So good evening. We are Core Solutions Group. I'm Ross. This is Karen, Josh, and Mustak. And we're delighted to be here to present our integrity proposal for the Solaire platform for the pressurized systems, that is. The proposal will follow the structure as shown. We'll firstly outline the current status integrity of the platform. We'll then explain how we assessed the ongoing corrosion risk and identify examples of corrosion that we got from this exercise. We'll then take you through the action plans, both short and long term, for maintaining integrity for the duration of service. And finally, we'll discuss the development for the new reservoir, which will involve the selection process behind the new pipeline and welding and testing requirements, and finally, the impact to the existing facilities. Karen will now take you through the integrity status review.
Thanks, Ross. Yeah, so just provide a brief overview of the integrity history that we have received and a few key focus points that we picked out from that data. So first of all, starting with the riser ESDV on field Z, so that's on the kind of far right-hand side of the slide. It's been previously identified there's preferential weld corrosion there. So we'd recommend doing a TOF survey to identify how developed that corrosion is, and then we can take that away and assess the risk specifically for that. Another point is the fuel gas pipework, which is at the top of the diagram there. So there was a loss of primary containment in 2021 due to external corrosion. So we recommend that we do a survey of corrosion under insulation to ensure that we don't see that mechanism again and have another loss of containment. Now onto the coalescer, which is just downstream of the third stage separator. So corrosion was identified internally within that vessel in 2015. A coating was applied. However, because there was only 1 millimetre left of corrosion allowance and it was suspected to be corroding at a rate of 0.2 millimetres per year, it's recommended that we do some ultrasonic testing to identify the wall thickness within that vessel and whether we believe that coating is actually providing sufficient protection. Lastly, on the diagram is our 16-inch oil export pipeline. So previous inspection data shows significant wall loss. So that's been identified through previous pigging campaigns. The wall loss or the wall thickness is now half of the original design, and that's resulted in maximum allowable operating pressure of the pipeline being reduced over time. So to prevent that being reduced further in future, we would recommend reviewing the pigging routine. So potentially doing biannual pigging rather than 5-yearly. And also to start injecting biocide as well, as it's likely due to water dropout in the line with the lower production rates and velocities, which have then caused the corrosion within the pipeline. Off screen, another thing we picked up was the stainless steel pipework that is in seawater service within the firewater system. So identified that as a key risk to pitting and crevice corrosion, and therefore, because that's in such a critical system, we recommend that as a key focal point going forward. So building on the integrity history that we were provided, we performed a risk-based assessment on the vessels and pipework, so 52 vessels in total, and we broke up all the pipework into 31 corrosion circuits. So we've done this so that we could then prioritise inspection going forward and identify the kind of high-risk items. So as you can see, we do have a bulk of them within the kind of high risk section. That's due to, I suppose, the poor integrity history on the platform and lack of data at this time as well. So that's something we would hope to refine going forward. I'll now hand you over to Josh, who will give you a few examples of mechanisms and the threats that the Solaire platform have.
Thanks, Karen. Right. So what I've been looking into is I've been looking into the RBAs, and I've gone through I've got a few example threats for you. They kind of cover different mechanisms that you're likely to see throughout the platform. So first of all, we've got the first stage separator. We've noticed that there was pitting, one large pit recorded at the bottom of the separator, and what we've put it down to is sand at the bottom because the sand removal is lacking. They're removing about 8 to 10 tons of sand at each shutdown. So the inhibitor that is in there is unlikely to work. And also there is no current biociding of the first stage separator. The next one will be the glycol storage tank. It's
not a hot storage tank, however, it is uncoated carbon steel and it's subject to deluge, I believe once every 12 months. And we don't have the plot plans of the platform either. So it could potentially be in a splash zone or just open to the elements in general. We've then got the produced water offtakes from the separators. These have been replaced with the duplex, as there was recorded CO2 corrosion, and also the nozzles were corroding due to sand erosion. But the one thing that they haven't accounted for is they've not removed the carbon steel valves, and there's also been no isolation kits noted to be fitted. So we'd like to fit some isolation kits just so that the carbon steel valves aren't quite at high risk. And this next one, this one's actually quite a key threat that we've identified. It's the fuel gas superheater. So it's working above 50 degrees and it's not coated, but it is insulated. So if the insulation is wet, then there's going to be a high risk of stress corrosion cracking underneath there. I'll now take you through some of what we've identified as a short-term action plan. So to start with, what we would like to do is we'd like to do a GVI of majority of the coated surfaces and insulated surfaces to look for breakdown. And once this is done, the areas that have been identified, we'd go further into them and do CVIs to build a plan going forward on the further inspection, such as MPI, DIPEN, UT, if required. We would like to biocide all of what the client have given us as biocided information. They've also told us that some things need to be monitored, and there's been no information saying that it has been monitored yet, so we would like to implement that too. Once we've got the environmental conditions of the platform, knowing the layout of where everything is, we can assess the atmospheric and the CUI risks a lot better. So that will hopefully reduce the risks and the likelihoods of some of the vessels and pipe work. As I said earlier, the sandwash facilities, none of the information we've received actually indicates that there's any online sand washing going on. It just indicates that there's the bulk removal of sand at shutdown. So we'd potentially like to review that so that we can avoid further problems such as the possible MIC that we've seen in the first stage separator. We'd also like to look through the gas dehydration system, because it's been noted that downstream of the contactor, there's actually potential upsets in the drying process, which obviously there shouldn't be. We've got carbon steel after then, and that's at high risk if the gas isn't dry. Now, once we've kind of done all of these things, we can look into actually building detailed inspection databases, looking for trunnion registers, CUI registers, all things that are a focus by the HSE at the minute, and also written scheme of inspections for all the pipework and vessels. And a few of the long-term plans that we've got is 2 of the hydrocyclones have been replaced with duplex due to CO2 corrosion because there was breakdown of the coating. Now, once we've monitored the hydrocyclones for a while, we would like to potentially implement duplex throughout the hydrocyclones if it's required, dependent on the inspection results. Yet again, based on inspection results for the GVIs and CVIs, we would need to repaint and re-insulate due to the age of the platform is 15 years old, and standard epoxy paint can last anywhere between 10 to 20 years, dependent on the brand. Also, as I mentioned earlier, isolation kits are a must to prevent any galvanic corrosion that have been identified through the RBA process. And just a little bonus, whenever the platform's in a state of shutdown, we would like to split as many flange faces to check for flange face corrosion, as this is a cheaper way of doing it compared to something like phased array. And also we would like to do a review of the nuts and bolts for stress corrosion cracking and also galvanic risk as well. I'll now pass you back to Karen for his part.
So for material selection for the prospective Sour field tieback. So before I go into the material selection, we'll just describe the criteria that we had to ensure the material could facilitate. So first of all, we have quite a high operating temperature, 110 degrees. We have partial pressure of H2S at about 0.5 kilopascals. We have 60,000 ppm chloride, and also because of the CO2 concentration, H2S concentration, we have a pH of just above 5. So combining the pH and the partial pressure of H2S, we end up in the sulfide stress cracking region of 1 in line with ISO 15156. So that's what's shown there on the bottom right-hand side. So what that then means for our material selection, our first option is to have a ISO 15156 certified grade carbon steel pipeline with sufficient corrosion allowance and chemical injection as well. In terms of welding consumables for this material, we would recommend low nickel content, less than 1%, so we don't get localized hardness, which would then be subject to sulfide stress cracking. And then we would do a Vickers hardness test on this as well to ensure that the material has a hardness within the limits specified for region 1. Another consideration that would require further review is whether or not we would need to insulate this as well to protect against top of line corrosion due to the carbon steel material. The pros for this option are it's low capex, it's carbon steel. However, the cons are because of the higher temperature, we may need to get certified chemicals, especially for this service and injection, and therefore that could lead to high OPEX cost. In addition, we would need to install an umbilical in Tutu as well to facilitate chemical injection, which may offset the lower capex of the material. And then also, because the carbon steel is part sacrificial, there is then a constraint to life of field extension should that be an option further down the line or any future tiebacks. Option 2, which is our recommended, is having a carbon steel pipeline, and just behind that is with an Alloy 825 liner. Commonly used with Alloy 825 is Alloy 625 for welding, so that would be our recommendation. The pros of using this or fabricating the pipeline from this are that it's corrosion resistant. Because you don't require chemical injection, you then don't need umbilical. And then also it would be suitable for life of field extension, which we see so often these days, which is great long term. The con, of course, is that it's a high capex liner material. However, by going for the option of a liner rather than a full CRA pipeline, we are reducing costs in that area. I'll now pass you on to Mustak, who will talk to you about welding and testing requirements.
Cheers, Gareth. So the welding requirement. So based on carbon steel, before we lay down onto the new field, we need to do is based on the low nickel welding, which is ideal for the sour service upgrade, which is fast, reliable, and it's semi-automatic. So that's before we lay down the foundation. We do the testing. On the impact testing, there needs to be 6 millimeters wall thickness. Hardness testing, or in the 10 Becker hardness test on the load on the well. Corrosion testing, minimum 24 hours, 40 degrees. And then we put that, do the TOF FD, time of flight diffraction, to have a good survey in place, have a good corrosion management in place. Before, then we review and implement the WQR certification, so we could track and trace. Yeah, so we could track and trace on the weld, and then review and monitor on the pipeline on well observation. I'm gonna hand that up to Ross to talk about the topside review.
Thanks, Mr. To assess the impact that the new field will have on the existing facilities, we started off by reviewing all the materials downstream of the tie-in point, pipework and vessels. And the overall finding from this was that all the pipework is compliant with ISO 15156. No issues were seen with the CRA pipework, which is duplex stainless steel rather, where we expect H2S in the system. And we also considered that with sour service, we'll need to continue to meet the export specification of 5 ppm Where a problem did arise was the first stage gas separators, which operate above the typical threshold for stress corrosion cracking at 80 degrees temperature wise. They're also 316 stainless clad. So the chloride stress corrosion cracking risk is quite high for these. What we suggest doing is qualifying the material under field conditions to Annex B of Part 3 ISO 15156. If this were not to be successful, we would recommend chloride inhibitor being injected upstream of the separators, and as a worst case scenario, recladding the inside of the vessel in contact with the liquid phase up to the high water at the high liquid level in the separators. Lastly, we've considered how we'll actually remove H2S from the system, and we suggest a low capex option of direct injection of scavenger either upstream or downstream of the first stage gas separators. We do recommend a full comprehensive study into the scavenger selected that's going to be tailored to the process conditions being seen. We'd also recommend a dynamic dosing strategy by installing an H2S analyzer upstream of the injection point and the necessary instrumentation so that this could speak to the downstream export H2S analyzer, and the dosing strategy could be optimized to save on scavenger costs. And lastly, we would recommend that a full H2S partitioning study is done for the whole system to take account of current production from field Y and also associated gas from multi-phase production. I'll now hand you back to Mustak, who will round off the proposal.
Cheers. So our closing recommendation. So all of those things you could get, you could buy for the platform. Well, if you hire us, we are ready to go in, do the GVR, CVR campaign, review on the biocide injection review, RBI implementation, which we could improve and maintain the corrosion management based on the recommendation. Our proposal for the alloy 825 pipeline, if we decide to go into our suggested recommendation pipeline, which we ideal, upgrade for the H2S scavenger for the better process, yeah. So yeah, so thank you for listening, and hope you enjoyed our presentation. Yeah, thank you. So I'd like to get the team over for questions. Yeah.
So thank you, gentlemen. So just on your proposal of direct injection of the H2S scavenger, had you considered any downsides of that?
The downsides, yeah, we do. So the H2S concentration is fairly low, obviously. Downside would be possible disposal, unreacted scavenger that needs to be removed from the system.
What happens if the pump goes off?
We'd have a reserve pump.
Okay.
So possibly multiple injection points, but yeah, 2 pumps, so that if one did fail,
okay,
we would have that.
I think the key is with the scavenger, as Ross mentioned, we do have dilution with field Y coming in, so the majority of the time we may not require it. It's maybe sometimes more for if that is a standalone field during outages.
Maybe missed that bit where you talked about cleaning.
Yeah, I think it was probably the last point. It was just because we're entering into the first stage gas separator, we
Right,
should have
okay,
dilution with field Y.
Thanks for the good another interesting presentation. Can I take you identified one issue around the superheater, which is 316 hot, not coated and insulated. So what are you going to do to mitigate the threat there?
First of all, what we'd look to do, we'd look to strip the installation, and then we'd be doing potentially just a UT survey to see if there is any existing pitting or stress corrosion cracking. There is potential for doing a dye pen to see if it has already cracked. And if everything is fine, then we would be looking at coating the vessel and then reinsulating the vessel.
You talked about pipe flanges, nuts and bolts, etc. Obviously, normally we try and avoid doing too many flange breaks during shutdowns, etc. Are there other ways that we could assess the data in advance outside of NDT, etc., to assess the likely risk of particular flanges, in terms of materials and things?
A good visual inspection certainly beforehand.
I think it's meaning before we even split it.
Yeah, just like looking at the materials of construction, etc., components of the flanges. Yeah.
Well, so we could look at the data sheets to see what kind of gasket's been put in place, because off the top of my head, I can't remember what kind of gasket it is, but if one of them has been put in place, then there shouldn't actually be much of a problem in between the flange. But that's as far as I can go with that without.
That's fine. Thank you.
Can I take you back? You gave some examples of some of the threats on some specific equipment, and you talked about separator and sand loading and sand. You're going to reinstate the sand washing system. So what are you going to use to flush through, and how are you going to make sure you don't introduce any new threats that aren't already there?
Well, currently, I think they're using seawater as the flushing, and it's raw, unfiltered seawater. So one way that we could do it is we could filter the seawater and potentially biocide it before it comes into the system, so that you're not reintroducing potential microbial activity, and biociding the actual separator itself as well. But that would require you to remove the sand for the inhibition to take place.
Once you've got water in that sand wash system, would you then drain it? Is there any risk of corrosion from having stagnant water within that?
Yes,
line?
so you would want to keep that as empty as possible, because stagnant water, obviously MIC propagates very well in that, especially around dead leg areas, and potentially trunnions.
I suppose the reduced water system as well is duplex predominantly as well, which protects us there. So our overboard route is.
So yeah, I see you've identified the 16-inch oil export pipeline as a threat. And you talked about pigging it and biociding it. Is there a threat that that's not going to get to the end of the design line, do you believe?
I think it's something that definitely needs closer review. I suppose a more recent pig would provide us with information of where the wall thickness currently is. But it's hopefully something that we can recover going forward, and we can provide support to you on that to help review whether or not we think it will last the remaining 10 years of life.
Okay, thank you. I'm not sure I heard you talk about corrosion inhibition as far as how well that's been managed. Did you consider that?
On
For the
the
CO2 corrosion, yeah.
For the oil export pipeline, or
Well,
in general?
for any of the systems, you mentioned some specific bits of equipment there.
Yeah, like the
systems.
coalescer, for example.
Yeah.
Yeah.
I just wondered if you'd considered CO2 corrosion and corrosion inhibition as being effectively managed, and whether that was the threat.
Yeah, no, it's a very good point. In terms of, I think that's probably part of, not just biocide injection review, chemical injection review overall.
Okay.
For the longer term piece as well, and seeing what we know there is injection facilities available for corrosion inhibitor. So it's just really reviewing those dosage rates and making sure they're applicable to our especially revised production rates as well.
Okay. All right. Thank you.
Thank you very much.
Thank you.
I think the the buffet is ready, so we can go have a half an hour break, and in the meantime, you can decide. Yeah.
How long have we got to convene afterwards?
So we are very tight with this schedule because we have to finish at 8:30.
8:30, got an hour.
Yeah, so we will go for the food now, and then you can come back maybe, I don't know. Yeah, yeah, if you can.
They've all focused on
Different
slightly
things.
different
Yeah,
things.
yeah,
Yeah.
yeah. There's only one of them that's so much they're going to cost.
The ups, the downs, and everything in between. Halifax, it's a people thing.
I'm Farmer Chris. Have a look at this. This is where Christmas dreams are made. Like these puff pastry mince pies made by Jess in Magic Oven. They're just normal ovens. Or this smoked Scottish salmon bit orange cranberries. Or this bourbony, bacony British gammon. It's like a big edible Christmas present. Sport more lads. This is why Morrison's is the only supermarket to be officially approved by me. Farmer Christmas. Right. Who's got the gravy?
This Black Friday, Stash is going bigger and better with this unmissable offer.
Outside, play more your wishes. Love affairs, backwards, wonderful journeys. And after you've done that for some time, forget that you were dreaming.
Okay, welcome back. I think this has been a very long exercise for you. This really started back in January when we started the actual individual presentations, and hopefully the idea was that you took what you learned during the year and really cemented that learning in doing this exercise. I mean, like anything, there's probably no single correct answer. And indeed, what we saw from all the teams with different things were picked out, different emphasis. And overall, I have to say the quality was excellent, really was. And I know that the judges here have had a really difficult time trying to separate the team. So I think the first thing we should do is you should all congratulate yourself on a fantastic job done. So well done. I have to say that considering the number of high risk and extreme risk, I just wonder whether any of you would like to go out to this platform. Next up really is to thank the mentors. So we have 6 mentors because each of them have been busy with the US teams, guiding you, steering you, mentoring you really. And hopefully you've appreciated and perhaps gained a lot out of that experience of having someone with a lot of experience actually given some of that experience back to you, and from that you can learn, and hopefully as a result you're all better materials corrosion engineers or whatever else you in your professional life. So the mentors, can we give them a round of applause, please? Can you stand up?
These pairs got some frozen. Morrison's.
Okay, and
magic. We're weaving some festive magic into your week.
okay, we've got certificates of appreciation for all the mentors. Steve Plant, unfortunately, is on holiday. Well-deserved rest. I think he's had a busy year.
Such a magic. Great. Weeknights at 10.
Great movies. Andrea Bocelli.
And then we'd like to thank the judges. Unfortunately, Stephen, because you had to stand in at late notice, we haven't got that one ready for you. But Sue, first of all, thank you very much for coming and spending time this evening in judging this competition. It's highly valued, I think, by all these participants as well. So thank you.
I'm back. Speak. You've got my attention. I'm glad that's fun up there. Yes, hello, Tucker. Where's George? I want to speak to George. All right, then I'll speak to you. Tell me, where's George? Okay, just over now. Come on. George?
So thanks. So now we come, and by the way, Stu and I have known each other a long time, so. Too long. So I've forgotten where I put the slip. So what I'm going to do is I'm just going to name the top two teams. Obviously, I'm going to name the second team first. So it was very difficult, and in the end, really, it was. I think if you're not named now, you were probably equal third, essentially. So it was that close. So, but the team that came second was Group 3, mentored by Bruce McKenzie. Well
County, but they don't have anyone else in the area. My phones are out, but I use since we're on the same.
done. I know, because I was here at the end. It was very tough to separate second and first. So the winning team is Group 5, mentored by Ali Reza. Okay, so well done. So if you'd like to come up, team 5, because I think we're going to call on the president of ICOR to actually present your prize, the certificates.
Good dog. Good dog.
Should there be one?
I was quite scared.
He'll be fine. He's okay.
We're gonna get this phone program. People are counting.
Yeah, he's fine. I wanted to have this back here. Taking you to the hospital is about liver twins. Smash it.
The backbone of this program.
Just plan that. Take it easy.
Modestly said that
You gotta cover this once.
I'm on that program, but
Give you a head.
it's been about 18 months of planning
Good.
into this. It's been
Sounds good. Trees
a
and
long
right.
process to get this up and running. We had a lot of help initially from London branch, who did the 3 previous
More of it look out.
program. So grateful to Trevor Osborne, David Moggs, and Ben Merkel for helping us with that. And we also had cross ICOR support for the lecture program. So there's 10 lectures during the course of the year. So we're grateful to all of those presenters that contributed to that. Going forwards into 2024, the next program will be run by Young ICOR, a Young ICOR division, which is all our members below 35. So our representative here from Young ICOR is Mei Ling. Yes, as I say, it's a very extensive process. We had over 50 applications from which we picked the 24 that presented tonight. So a lot of work's gone in behind the scenes to get to where we are today. So I'd very much like you to give a big hand to those here and online to show your appreciation. Thank you.
George, when you're finished eating, just feeling afterwards, we got something we need to do.
Just one final point. The perhaps unusual this year, we had a very wide range of backgrounds, people from 15 different companies of quite a range of disciplines. So to get all this coordinated into these suitable groups and working together is on behalf of the and all the Aberdeen committee. So I thank them all for that. Thank you.
I know we've never talked much about your dad, but
Last but not least, very much indebted to Subsea 7, who loaned their training facility over in West Hill. So all the face-to-face lectures were held at Subsea 7. Some of those were hybrid, as you know, and very grateful to them for making that.
You want to press B, Turner? Go ahead. You ever trust Craig again? Anyone else for that matter? You're dealing with me. Do we understand each other?
What's next to him?
What's on me? And we was tough.
Which bit shall I repeat? Yeah. Once again, many congratulations to our winners, Group 5 tonight, and special thanks to all the others who came very close. There wasn't a great deal of difference between the groups, so just be aware that you have put a lot of effort, I can see, into what you did, and I'm very conscious of the engagement that you had in the process. So very, very much appreciate the overall engagement. So thank you. And so just can I just briefly introduce Dr. Young Gale. He's our new Vice President who will be working with myself as the new team for the next 2 years. So for the been a BP for several years, have been our main sponsor for the YEP program. So please again give your hand of support to BP for sponsoring the main prize, which is obviously the visit to the NACE conference, which next year will be in Colorado, I believe, in March. Denver, Colorado, March.
Come on in. Hi, Frank. Merry Christmas.
Well,
I don't want to bother you. We're not bothering.
yes, currently we've had 2 retirements from the Aberdeen branch, so we're currently looking for new younger members to join the Aberdeen committee. So we've currently got 2 vacancies. So if any of the current YEP candidates would like to join the committee, take part in our programs, then please see Dr. Mohammed Ijaz just here.
A lot of traveling. Long stretches.
So you wanted to say?
I just wanted to say, I hope you all had a bit of fun doing that. And yeah, having operated this facility, I know how challenging it is. Not quite as bad as it's been painted, but some of these were real scenarios that we struggle with, and we're still struggling with. But yeah, I hope you all had a bit of fun, and thank you so much for all standing up in front of us and presenting. It's been really, really good. So thank you. You should all be proud of yourselves.
Don't beat yourself up, Hunt. We all make mistakes now and then. Your daddy and me,
Okay.
He's waving.
Hello, Chris, can you hear me? Hey. Hello, everyone. Show your attention, please. We want to get a group photo of everyone before we go, please. Take a photo. Right. Come over this way, please.
I'll ask me what I thought about the I give you a hand milking. I was, I was here. See, it's brown or white.
One. How about yourself, CJ? Take a selfie. Last one for the road.
What would you say if I said that? I'm thinking instead of moving to Minnesota, I should stay here with Grandma and Grandpa. Oh, that's the thing here. And maybe you need to be here where you can feel closer to your dad. Okay, there.
Let's see how
Dad had his accident.
So you check all those ideas that.
Yeah, it's not doing, I know. Yes, no, no.